Hi everybody, my name is Brad Conrad. I'm the director of the Society of Physics Students and Sigma Pi Sigma, the Physics and Astronomy Honor Society. And I'm really happy to have you all join us today. We're here for a really awesome reason, and that's for the 16 interns that were with us for 10 weeks over the summer. So if you're an intern, would you mind standing up? And can we get a round of applause for these folks and their hard work? You may now sit, thank you. I want to say a couple words about the intern program itself. So the intern program is unique. There are a lot of really great intern programs, especially in Washington, D.C. at national labs, down on the Hill, a lot of great places that physics students will work. But ours is unique in the sense that there are 16 interns, and each intern is doing something different over the summer. So there may be 3 at NIST, but they're doing vastly different projects. There's 2 on Capitol Hill. But they're all working in very different environments, from writing to researching to doing outreach to communicating. But they're all living together on the campus of George Washington University, and they get to share their experiences. And I think we'll get to see a little bit of that today. And so one other thing I wanted to mention is that this program, while it's supported by the American Institute of Physics and the 10 AIP member societies, it's also supported by donors. So really, for the students in the room, you're here because people who were just like you a couple of years ago, or more than a couple of years ago, really felt it was important to have you doing this job over the summer. So, well, I know I have a couple donors in the audience, but I just wanted to say thank you to everybody that donated to the program, and I hope that you found it as awesome as it was on our end to run the program. So, thank you for all being here. I'm really excited to hear your talks. I've only heard a couple of them, so I'm excited to hear the rest of them. The format today will be 8 minutes plus 2 minutes of questions. At 8 minutes, I will remind you about your time, and that way we'll have plenty of time for questions. We'll take a break at about 11:30. And I would like to introduce Liz. Come on up. And Liz is going to make some remarks on behalf of AIP.
Hello, everyone. I'm Liz Darkaran, Chief of Staff at AIP, and on behalf of AIP and the AIP Federation of 10 member societies, welcome and thank you for spending your summer with us. It's truly a special time of year where there's a lot of excitement, activity, enthusiasm, and having the interns here is a reminder of why we do what we do. Truly, thank you for that. We sort of need that shot in the arm every summer to help keep us going for the rest of the year. It takes a village. It really does, to raise the next generation of our scientists and to help advance the physical sciences. When I say it takes a village, all of the mentors, all of the organizations who accept interns, who give mentors and mentorship to the interns throughout their experiences, really help shape the future of the sciences. So I thank the organizations who work with AIP. It is an investment, and they get a lot out of it, but they also put a lot into it. So thank you so much. I just hope that when you are advanced in your careers, that you take the time to mentor students as well and have them follow in your footsteps. So with that, I will turn it over to the interns.
Hi, my name is Justin Andre Avendano. I'm currently a student at Stevens Institute of Technology, currently studying physics and minoring in computer science. I came to the US mostly to study physics, but I always make sure to bring my culture around with me everywhere I go. This summer, I stayed with the Soft-Minded Kitchen and the Society for Rheology in order to help with their mission, to create rheological outreach material for people like us to further understand what rheology is. So then you might be asking the same question I had in the start of the internship. What is rheology? Rheology is the study of the flow and deformation of complex materials. When you think about it, things like water and whipping cream have very different ways of interacting. Whipping cream is a form of non-Newtonian fluid, meaning it acts in a different way according to different stress rates. So if we look at this video here created by my mentor, Arif, you can see the honey on the left and the whipping cream on the right flow very differently. The whipping cream on the left doesn't break on its own weight and holds like a solid, while the honey drips like almost instantly. If you look at this video right here, you can see that the whipping cream and the honey act differently when we have something slide on it as well. the whipping cream almost instantly slides out while the honey doesn't. That's why today, I wanted to show you guys what I've been working on this internship, and it's something we call in the Philippines, maja blanca. So what is maja blanca? Maja blanca is this coconut pudding created with like coconut milk, corn, and we top it off with different toppings, such as coconut shavings, cheese, and something I put on top there called latik, which is sweetened reduced coconut cream. The word maja blanca came from a Spanish word, maja meaning delicacy, and blanca meaning white. We usually eat this during Christmas time or sometimes on your birthday. So in order to create maja blanca, you will need these ingredients, and the ones I want to focus on are the coconut milk and the cornstarch. The one I have for you today is the vegan version, only using the coconut milk and the cornstarch. So while I was making a version of the maja blanca for the interns, I accidentally added too much cornstarch to my mix. And it ended up creating like this goopy kind of liquid thing that acted like a solid, at the same time a liquid, depending on how I like touched it. And so this made me question, why does adding too much cornstarch create a non-Newtonian fluid? Because the coconut pudding I made almost acted like oobleck, which is a water and cornstarch mixture, where if you hit it, it feels like concrete. So I got down to like the science on why this was happening. This is an example of what happened when I added too much cornstarch to the coconut milk. It created like this dough kind of thing, but it would also act like liquidy depending on how I would pull it. And when you pull it, it feels like dough, and when you punch it, it feels like concrete. Same thing with like the water oobleck. This is a version of the oobleck where you'll notice I have a hard time grasping it. That's because like it feels like a solid, and then once I release it from my hand, it turns back to a liquid, which is like insane on why that happens. So what I did was I tried to experiment. Is it really the coconut milk at play here creating the non-Newtonian fluid, or is it the cornstarch that's like creating this weird enigma of liquid? So I made two versions of oobleck, one that is a 1:1 and one is 1:2, which is the normal oobleck. So if you look at this bowl over here, I have a version of the 1:1, and it's very weird because when you try and grasp it, it's like very murky, at the same time like milky, and like when you try and make it flow out, it's almost like water, which doesn't make sense because this worked for the coconut milk. So why was it flowing? Why is it flowing like this instead of it being like a super solid? Because like even when I grasp it, I can't really grasp it. It's just like liquid all the way. So the reason for this is because of the microstructures within cornstarch and water. So here is a visualization of what it looks like inside the microstructures of oobleck. This is the 1:2 version. So you'll see that there's like a lot of cornstarch, and that's because we have a lot of cornstarch, around 2 cups of cornstarch versus 1 cup of water. And if you compare this to the 1:1, there's more space for them. So they can't really, even if they're on a random walk, they won't really hit each other. They won't jam and pack towards each other. The reason why it works for coconut milk is because coconut milk has a lot of fat. Around 24% of coconut milk is fat. Compared to normal milk or cow milk, it's around 3% to 2% of fat. Comparing all of this to water, which is absolutely nothing besides the H2O in it, coconut milk has these fat globules that are on there, and they take up a lot of space, and they're pretty huge compared to the cornstarch molecules. So then they take up this lots of space, and then when you pour in the cornstarch doesn't have anywhere to go besides the crevices in between the coconut milk. So then this creates an oobleck, or like a non-Newtonian fluid with less cornstarch. So in conclusion, some characteristics of non-Newtonian fluids can be observed in both coconut milk and water cornstarch mixtures. Coconut milk shows non-Newtonian behaviors at very low concentrations, and non-Newtonian behavior is due to the microstructures of the cornstarch jamming and packing on each other. So whenever you're trying to make maja blanca at home, like just because you want to impress a friend or like you want to try more Filipino culture, don't end up like me and trying to cook whatever that was. Because that tasted really bad, and that's a real reaction. I almost gagged trying to eat the cornstarch I made. So yeah, I hope you guys enjoy the taste of what I did during the summer. And if you want to see more of the projects I did with the Soft Matter Kitchen, I helped a graduate student with her project as well. You can check out the Soft Matter Kitchen's YouTube channel and their website, as well as for more physics content, you can check out my YouTube channel, The Avendano Effect. Thank you.
Anything you'd ever want to know? I have a question.
Yeah.
So why is it a non-Newtonian fluid? Like, why is it called non-Newtonian?
That's a good question. So let's put it this way. A Newtonian fluid acts in the normal way the Newton's law would act. So if we have, for example, the second law, force equals mass times acceleration. So when we have some object moving at a certain acceleration, that should have a lot of force depending on how much mass it has. So when you have this liquid that's like both, that's just on its own, it acts like it should. So for example, let's say the juice that Kayla has here. That's an example of a Newtonian fluid because under its own mass, it still has a consistent amount of force. While a non-Newtonian fluid, like the gel that she has there, it doesn't have exactly a linear force that occurs, and depending on how much stress or force you put onto the liquid, it changes its properties. So then, for example, the gel, it would create like, if you try and like squeeze it out, it will flow like a liquid. But if you just like top it over, it will just stay there. Same with like ketchup. You notice like ketchup, you have to do that, right? That's the same reason, because like the fluid is still not acting in the normal way, if that makes sense.
Thank you.
Awesome.
Another question?
What's your favorite non-Newtonian fluid you worked with this summer?
What's your favorite non-Newtonian fluid that you worked with this summer?
So I worked with a lot. I worked with mostly pudding. I also worked with noodles, souffle pancakes, what else? Mousse. Honestly, my favorite was either the maja blanca or the noodles. So Lucy helped me out with the noodles, and that was a nightmare. But it was really fun to see like how the noodles could like change its properties depending on how much water and oil you add. So if you add too much water, it becomes a solid. Oh, sorry, if you add too much water, it becomes a liquid. But if you add just the right amount, it acts like a non-Newtonian fluid. So there's like a Goldilocks zone in between the noodles. While maja blanca, I mean, it's just fun to eat.
Round of applause.
We're good? Perfect. Hello, everyone. This is going to be a little change of pace from Justin's presentation. But I'm Taylor Overcast, and I was the American Association of Physics Teachers intern for the summer. This is a discussion that I actually was able to give at the national conference in Michigan over the summer, and it was originally about a 40-minute presentation. So this is a very condensed version. But it's on the long-term impacts of attending a low-income school. And specifically, I want to examine what low-income K through 12 education looks like and how that leads into a four-year institution, specifically for low-income students studying STEM. So start off by defining low income. So low income is defined as 80% of the median family income for the area, while very low income is defined as 50% of the median income for the area. In addition, low income schools are going to be discussed, and a low income school is defined as a school with at least 50% of its students on free or reduced lunch. Free or reduced lunch is given to any student that is at 185% times the poverty line or below. And the reason that this definition is so important to understand is because it's a very regional specific definition. So it goes from county to county instead of looking at a national base. So it takes into account average cost of living, things of that nature as well. So 5 things that I want to point out that hardships of low-income students additionally face compared to affluent students. So first off, cost of school supplies. This is extremely applicable specifically to physics due to lab fees. In a lot of low-income districts, they can't afford to pay for their school's lab fees. Therefore, students are expected to pay that fee for themselves. And that often leads students to go into humanities. Also, amount of sleep. According to the American Psychological Association, low socioeconomic students often have less sleep. This can be due to parents' work schedules or their own work schedules. In addition, they're lacking technology. This is purely just due to cost. This might be a lack of resources such as a laptop or a desktop of some sort, and also it could be internet access. They're also going to have a lack of extracurriculars. This is often due to either having to have a job or just due to transportation issues. They're relying upon the bus due to their parents' work schedules, things of that nature. But the one I really want to hone in on is a later start to education. And you might be asking the question, why is preschool important to four-year institution education? 41% of low-income students were enrolled in preschool, as compared to 61% of affluent students. Now, this was a longitudinal study done in the 1960s, 1970s, and 1980s. There's 3 separate projects here, and they were, the students were monitored over the next 40 years of their lives. So these are known as the Big 3, and they were done quite a while ago, so this is very well thought out and seen very far down into the future here. So these students were split into 2 groups. They were all low socioeconomic status groups, and they were split half into a control group and half into the preschool program. 3 different preschool programs that were designed in a different ways with different costs up front. And as you can see on the data here, all 3 programs resulted in those students having a longer a higher graduation rate, as well as staying in school longer in general. They also had a lower criminal rate, as well as lower pregnancy rates within teen age range. They also had higher income jobs. So in result, based off that higher income job, these students were able to pay back more than what was spent on them through the program. So moving forward from preschool onto more like a high school level here, this is some ACT data. So ACT is pretty nationally well-known thing. It's scored on a point scale up to 36 points. And as you can see here on the data, the blue line is comparing students that fall within the low income bracket compared to very low income bracket, while the orange line is representing affluent students compared to very low income students. And if you can see on the chart here, low income student scores on average about 2.5 points higher on the ACT compared to a very low income student, while an affluent student scores about 4.5 points higher on the ACT. This on average, just comparing average low income to average affluent, is a 3.84 out of 36 point gap. That's over 10%. And so really this is, in a way, almost cyclical in the nature of students that come from high income are going to be able to get higher scholarships and get into higher ranking schools, because this is critical scores to get into college. So this also has implications upon the teachers that are within these schools. So it was stated by the Learning Policy Institute that turnover rates for mathematics and sciences are over 70% higher for a Title I school. A Title I school is a school that has at least 40% of its students qualified as low income. And these teachers were all mathematics and science teachers. So STEM subjects are especially hit by low income districts, which is just an interesting little tidbit. And this relates farther into my presentation, so we'll come back to this. So moving on to physics now, as you can see, 2019 was the highest enrollment rate for all physics classes nationwide. This is within high school level physics. So looking at, this is the American Institute of Physics data. And this looks really encouraging. However, whenever upon closer look, this is also the time that the lowest amount of schools have ever offered physics. It's down to 84% compared to, in 2005, being 93%. That's almost a 10% decrease over the last 15 years. The reason that this is important to notice is while enrollment is at an all-time high, the amount of schools offering it is at an all-time low. These schools that are still offering physics are going to be larger schools, and they're often going to have areas of parents and educators with a higher education themselves. Higher education often implies higher income. So higher income districts are going to be able to give their students, especially physics education, which in turn is going to give them a better shot at going to college themselves. So higher education areas are going to remain higher education, while lower income areas and lower education areas will remain that. And this is just perpetuating the opportunity gap that's already so prevalent. So moving on to actual enrollment within institutions as we know it now. I really want you to take a look at the yellow line, or gold line, here on the graph, and that's representative of a 2-year institution. These show the data from the National Student Clearinghouse Research Center over 2016 to 2018, just to show that this is a continuous problem. It's a consistent problem. It doesn't change from year to year. And the only type of college that low-income students are more likely to attend is a two-year university. This is most likely due to cost. 2-year institutions are often much more affordable. However, that often tops this student out at an associate's degree in a lot of terms. So that's applicable to STEM especially, because whether it's classist or not, on all the occupations that are representative in our nationwide career database here, according to the U.S. Bureau of Labor Statistics from 2015, the left-hand side represents all STEM occupations, while the right-hand side represents all occupations. Everything below the bright green is just an associate's degree or lower, while the bright green forward is anything bachelor's and beyond. And as you can see, STEM is especially heavy on bachelor's and beyond. And so that means that even if it's just expected based off a classist situation here, that students that are lower income and more likely to attend a 2-year university think that going into a STEM occupation is less likely or less attainable for them. So this is STEM completion adjusted numbers. So I took all the data that was represented in National Student Clearinghouse, put it into an Excel file, reran the numbers so that affluent students were had the same representation as low-income students within the data. And from that data, I was able to collect that STEM degrees for low-income students are about 7% of all those students will one day get a bachelor's in a STEM field, while 15% of all affluent students will attain a bachelor's in a STEM field. That's over 2 students that are affluent compared to low income. That's a huge number that should definitely be addressed. Specifically, going back to the teacher retention rates, I want you to notice that engineering, math, and physical sciences are much lower for low-income students. These are the subjects that would most likely be affected by that teacher turnover rate. So, in conclusion, low-income students have several additional challenges to attend a 4-year institution. They have a lack of resources such as experienced teachers and early opportunities such as preschool, and this results in lower test scores, making it harder for them to get good scholarships and get accepted into high ranking schools. So thank you, and questions.
Questions?
So you said that the number of students enrolled in physics has increased.
Yes.
Is that relative to the number of students?
Yes, it is. The amount of population overall is not growing as quickly as the amount enrolled in physics is. So it's a higher percentage.
Okay.
Yes.
Questions? So I had, go ahead, second follow-up.
Also, what's a longitudinal study?
It's a study that occurs over several years. These were specifically over 40 years.
So I had a quick question. So you looked at some really eye-opening data. What's one thing that could be done to help overcome what we're seeing in the data?
Yes, I really appreciated that question because that was actually something that I addressed in the 40-minute presentation. But early education. So as you saw from the data, the preschool program is paid back. While it's a huge investment up front, it is something that we should consider to invest in the future because it helps everyone out. It helps the government out based off taxes, and it helps those students out to actually have success. Yes.
Thank you.
Thank you.
Okay, thank you so much. Hi, everybody. My name is Taylor Colisie, and this summer I intern at NIST. I'm a rising senior at Washington and Lee University in Lexington, Virginia, and I'm so excited to share with you today about what I researched with my mentor, Dr. Charles. So we were trying to find ways to detect really small signals buried in noise and other distracting waves were present. Well, this is a very common problem in experimental physics. You have this interesting phenomena you want to study, but there's all these other competing factors that just make it very difficult. So what do scientists usually use to combat that problem? Well, one of the common technologies is the lock-in amplifier, shown here with a blue square. This works by you send in a small noisy signal, but you also encode a little information into that signal called a reference. You do it through a process called modulation. And as long as you have that reference, you can use that to extract your noisy signal and end up with a clean, strong, all the data that you wanted. Here's an example of a lock-in amplifier used in the laboratory I worked in. I've listed some drawbacks because while this machine is great in the laboratory, it has some downsides. What if you wanted to bring your experiment outdoors or portable and take it across the country with you? What if you wanted to do this in several places at the same time? You would probably want it to be cheaper. So just some examples of that when you're using a lock-in. On the left-hand side, we have an experiment, electron spin resonance. Right now, we are working on a way to detect how much radiation someone had absorbed in their body, like their dose, through their credit cards or their driver's licenses. And so to do that, we use electron spin resonance, which uses magnets. And you can imagine these electrons have this teeny tiny magnetic property compared to all the big magnetic and electromagnetic waves around us. You would use a lock-in amplifier for that. Another example that you might be able to picture more often is imagine you are trying to find your pulse with a pulse oximeter. Those are those little clips you get at the hospital. They go on your finger, and you can measure your pulse and blood oxygen concentration. They use light. But you're in a lit room, so how do you tell those lights apart? You can use lock-in detection there as well. If we wanted to make our lock-in amplifier even smaller, we've thought, what if we could use a radio? You know, radios already do this. They take really weak signals that barely produce a small micro voltage kind of deal with an antenna. They can discern a particular frequency out of a whole band spectrum of them, and it can amplify this as useful information. And I've input a couple comparisons to how much this particular radio, the SDR plate RSPDX, how it compares to a lock-in amplifier, and the cost is 1/14. Specifically, the dimensions are really tiny. It's 1/60th the size. It's crazy. And also, it's software defined, as I've listed at the top. That means that the internals are controlled by the user. You can pick exactly how to configure your machine to do just what you need it to. Whereas a traditional lock-in amplifier is pre-configured by the manufacturer, so you have less flexibility. But with all this flexibility, there's got to be a cost. Maybe your program one's really slow and it's so complicated it takes years to learn and master. Or you can never make a measurement and see it real time because you have to process everything over a few minutes. Well, luckily, the open source community has found an alternative. GNU Radio. This is what we've been using in the lab. And I'll give you just a visual of what it looks like. The magic of this software is that while it's simple to use because it's just a graphical user interface, and there's hundreds of function blocks you can put in, wire them up with little connectors, and then just see how it runs. What's so wonderful is it's written in C++, which is a language that can be more optimized than a more higher level language like Python. But while it also has that, it has a Python interface option. So you can write your own code in Python, which lots of scientists are already learning besides C++. So that increases how your skills might be applied to this program. Just to give you an example of what this program can offer you is while you're using your radio or your measurement device, you can make plots at the same time. For example, at the top left, we have a time domain plot. It's basically time axis on the bottom and voltage on the top, or amplitude. This is like what you might see on an oscilloscope. The top right, this is a phase diagram. It can show you how your signal, how two signals are varying in phase with respect to each other over time. And the bottom one is a frequency graph, like Fourier transform. And you can do all of this simultaneously without any appreciable, noticeable loss, and synchronization using this fantastic software. So to push our little radio, we want to see how well can this thing actually do a lock-in amplifier's job. And well, we tested it, and we found that while the radio is usually designed to give you an output at around 44 kilosamples per second, because that's it's basically the Nyquist frequency of what humans can hear, we were able to push it to 1 million samples per second, which is incredible. And we realized that was pushing our computer to the limit. We were going so fast we could hardly transfer the data to our computer. And so that was an interesting bottleneck, and hopefully we can get through that in the future. And so since our sample rate may be limited by the hardware, if we can take many samples of a periodic signal, one where it repeats after a certain amount of time, if we take several measurements and layer them on top of each other, take an average, maybe we could get an even cleaner signal at the output by reducing all that noisy bumps and blemishes along the way. So we've actually implemented this. These are graphs that show the sample index along the bottom. Let's say you have 100 samples, and you repeat that 100 for every period. The vertical is the amplitude. So we've actually shown that this is possible. But unfortunately, it doesn't work in GNU radio. So we've had to export our data and in real time try and fetch the data, process it, do all these things. It works, but we lose that synchronization aspect. And that's something that we're working on improving in the future, just to make our product even more robust. And I want to thank you so much, and I want to say an express of gratitude toward my mentors and those who are helping me out here. And I hope you all have a fantastic day. Thank you.
Questions for Taylor?
So, do you mind just going back to the previous slide that has the graphs on it?
Yes, absolutely.
Yeah. So why is the amplitude on the so-called strong output? Why does it appear to be so much smaller than the maximum amplitude on the noisy output?
That's a great question. So on this noisy, so the way that these graphs were created, on the left-hand side, the noisy input was a 1. It was a sine wave with an amplitude of 1. And you could say 1 volt, but this is in software, so it's just 1. And our noise had an amplitude, maximum amplitude of 1. So at some points, you see 1 plus 1 is like 2. Or 1 plus 0 is just 1. Or you can even have a negative noise, things like that. So that's why our noisy signal was kind of jumping all over the place. Whereas once we average out the noise, we get closer to a 1 amplitude sine wave. Yeah, great question. Thank you.
Other quick question? My question is, will this ever be used on the credit card thing or the ID thing that you talked about at the beginning of your talk?
So we are currently working on making that a reality. We've already been testing our radio with real-world signals that come from our function generators and our oscilloscope. And we've been able to, what's super fascinating is with radio, you can have several inputs at once, as many as your bandwidth can allow. And so we've already developed the methods for testing it with these credit cards. We just haven't gotten there yet. We're super close, though.
Thank you and great job.
Hello everyone, my name is Shamria, and I'm a senior at Colgate University. I'm a physics and chemistry double major, and this summer I worked with Dr. Sujitra Pupanratana in the nanoscale device and characterization division at NIST. So, my work involved basically helping enhance the capabilities of the instruments we have in our lab, and helping measure and standardize ways to measure electronic properties of certain sample surfaces and devices. Most of this research was motivated by future research in semiconductors, because in order to improve that technology, we need to develop and improve existing methods of characterization. My work was split up in 2 parts. firstly, I'm going to talk about the electrical measurements that we did on the probe station on the left. So the probe station serves as a platform for testing devices. So the device goes in the golden chuck on the center, and it's connected to the probe tips and then the micro positioners, which can be connected to various instruments, and we can perform our measurements, such as making current voltage graphs or capacitance voltage graphs. I'll talk about the PEM later. So the instruments I worked with this summer were a power source and a system electrometer, which worked in conjunction to act as a source measurement unit. Here, the power source provided a voltage or current, and the electrometer could measure the current voltage or resistance. I also worked with the LCR meter, which can sweep through a range of frequencies or voltages while measuring impedance values such as capacitance or inductance. So to get this working with the probe station, we used an open source Python library called PyMeasure. The reason we used this over commercially available software was a higher degree of customizability and control. This controls the instruments using the SCPI command interface, which is a universal interface for electrical instruments. Some of the instruments were not natively supported, so I had to initially add support for them. Once that was done, I wrote Python code to add functionality such as various different modes and changing parameters like integration rate and sequencing on the fly. I then also added a user interface so that the user could see what was happening and take their plots in real time and compare their measurements. I also added documentation to the code so it's easier for people who come after me to use it and customize it. Lastly, the work involved a lot of testing on the probe station, so we tested and calibrated the instruments with various devices to ensure that it worked. So for the source measurement unit, we started off with testing resistors to make sure that it was accurate enough, and we found that was accurate to about 0.1%, which is great. Next, we moved on to a metal oxide semiconductor device and took current voltage graphs there as well. We tested different squares of different areas and normalized it by area so they kind of overlap. And this compared well to plots we had already made using a commercial probe station. Next, we tested a gallium nitride diode, mainly to ensure that spikes or large spikes in our measurements still function with the instruments. For the LCR meter, we performed similar measurements, but instead of current voltage, we were sweeping a voltage and measuring the capacitance. For this, we used, again, a metal oxide semiconductor device because this has characteristic properties that we were looking for to test. So there is this phenomenon called accumulation and depletion, which happens in MOS devices. Basically, the semiconductor layer at the bottom can develop its own capacitance at certain voltages, and we see this behavior. And yeah, that matches up pretty well from what we expected, which is great. Next, I'm going to talk about the photo emission electron microscope. So this is a form of microscopy that is based on the principle of photo emission. So a light is incident on a sample surface, which can then emit electrons. And these electrons can carry a lot of information, including like kinetic energy, which can help us visualize the surface. So my goal this summer was to modify the sample holder such that it can accept additional electrical contacts, which we can then apply to the sample surface. And this could help us visualize how the charge carriers move within the surface, which is pretty cool. To do this, I first had to model the sample holder, which is very small, in AutoCAD. So these designs are precise to about 0.1 millimeters because everything has to be very mechanically stable and fit in. So it has 6 separate components that go on top of the sample. So the washers help insulate the device, and the retaining ring and the spring plate keep everything in place. The sample holder itself then goes on the PEM shuttle. This has electrical contacts in the outer green tube. It also has other electronics, but the electrical contacts come out of the front, and currently they're being used for a thermocouple, but we plan to divert these into the sample holder so we can then connect it to the sample. So I added a couple of holes at the front so that we could do that. Next, I also designed a printed circuit board for the sample holder, so it was easy to reuse, and you could switch out samples on the fly, and it was stable. So what you see there is the schematic and on the right, the sample goes in the center, and we can use wire bonding to attach the sample to the copper pads, and it's very symmetrical, so any orientation works. One of the main concerns with this was that the PEAM has a very high vacuum in its chambers that it needs to operate. It's equivalent to that in outer space. So to prevent outgassing, which is a phenomenon where the dielectric has gases inside, and because of the high vacuum, these gases are pushed out and can ruin the electrical conductivity. So to do that, we had to research ceramics and vendors that would support these high pressures, or low pressures, sorry. And we ended up going with a ceramic-based composite for the main material. Lastly, this was designed to fit in the sample holder, so it's pretty small and it goes underneath all the components. Okay. So overall, my work this summer consisted of getting 3 instruments working with the probe station, adding the documentation to make it easier for other people to use it. I also modified and modeled the PEAM sample holder and designed the PCB for the electrical contacts. In terms of future progress, we can definitely add more functionality to the instruments. And we didn't get around to testing the PCB and sample holder, which we'll do in the future. Thank you all for coming. Thank you for listening. Any questions?
Great job. Questions from the audience?
What was your experience like working in a lab? Is it something that you would want to do more?
So I've worked in a lab before, but this was pretty different from other experiences I've had because I was working with people, including my advisor and the other people working in the lab, and like the collaboration was very helpful because I feel like I learned a lot more than I would just working alone, and it was definitely nice to get used to all the instruments and yeah.
So, quick question. What was the coolest part about working at NIST?
Definitely the campus and the environment. So like all the research advisors and mentors are like, very helpful and they want you to learn. So that was really cool to see. Like people want to, teach and do science. It's just, yeah.
And then one last quick question. What's one thing that you learned going through this summer experience? One research fact or science fact that you'd like to share?
Electrical testing is a lot harder than it looks. So, yeah, there's a lot that goes into it, mostly time and yeah.
Round of applause for a great talk.
Okay. Hello, I am Valeria Terry-Fluker. This summer I've been working at NIST in the nanoscale spectroscopy group under the mentorship of Jared Wallstrand, and I've been working on taking precise measurements of the optical current effect and 2-photon absorption in gallium phosphide. So before I get into the weeds of what my project was, I want to take you into the lab with me so you have some context on what I've been doing. So here on the far side, we see a picture of me in the lab, like earlier this week, standing in front of most of the experiment. So we're doing a spectroscopy experiment using pulsed laser light. So there's going to be a lot of short pulses of laser light bouncing along all those mirrors. On the picture on the that's closer to me, you can see me installing a sample of gallium phosphide, which is the material that we're investigating, into the path of the lasers. If we zoom in onto the circled part, we can see the sample. It's an orange-looking semiconductor. So what you just saw is a new experiment that has been basically recently designed to measure some optical properties that are not often precisely measured, or if they are, it's only like a couple data points. So we're trying to get a lot of data very precisely. And I've been helping to test the feasibility of this new type of experiment, which I'll explain in the future. This gallium phosphide is our first test material. So the reason we're using gallium phosphide is because it exhibits interesting properties in the wavelength ranges that we can test pretty easily with our setup. And the knowledge of these optical properties of that material can help it be used in integrated photonics in the future. Integrated photonics is like integrated circuits, but with light. So it's like a chip with small optical things that can do cool stuff like integrated circuits do. So now to talk about the material gallium phosphide. It's an indirect band gap semiconductor. So what that means is to excite an electron from the valence electron to the next available energy state, you have to provide it 2.4 eV of energy. But you also need to provide a change in momentum. So it needs a photon and a phonon to simultaneously excite it. Unless you can provide a photon that has a lot of energy, so 2.8 eV, to bump it all the way up straight. So that's a lot of energy for a photon. So typically what's going to be happening in an actual experiment or an actual application is you're going to have light with lower energy, but multiple of them can simultaneously be absorbed. So one of the two numbers, properties I said I was measuring is 2-photon absorption. So that's going to contribute to loss in material. If your material is absorbing light, that's going to, you're going to lose light. So it also has a really high refractive index. It's transparent from visible to long infrared, so it can be used for optical devices in that regime. And it also has a large Chi2 and Chi3 coefficient. What that means for us is that the refractive index of the material changes with not only the wavelength, but also the intensity. And that change with intensity is pretty big compared to other materials. That nonlinearity is what's useful in integrated photonics for applications, because different nonlinear effects are going to give you a material, a bigger toolbox for what it can do, and what people that are going to engineer these kinds of devices can have done. So this is an example of a gallium phosphide ring resonator. What I want you to get out of that is that that's a photonic device, and it's 100 micrometers total in length. These things are very small, and I'm just trying to understand and measure these properties so that it can be used in the future. So that's the background. Next, I want to tell you what I did. So I helped set up the experiment itself, and I was working with all the mirrors and things you saw in the first picture. And then I also performed derivations because it took me a long time to understand the process from the data to the actual values. So I spent quite a bit of time doing math. And then I also wrote code in Julia to help process all the data. We're going to start by talking about the experiment. It's called a pump probe spectral interferometry experiment. And we're going to introduce this by starting with just the pump probe part. What that means is usually you excite something and then see what happened. You excite it by sending in a short pulsed laser beam, which is represented by the red thing. And it's going to excite a material into a transient, so a short-lived state, where what it's going to absorb and what it's going to have a change in refractive index is not what it would normally be. You investigate that by sending in a second pulse, which is called the probe. And the probe is going to be like a supercontinuum, so it'll have a lot of different wavelengths in it. And then when it goes in there, a certain time delay later, parts of it will be absorbed, parts of it will be slowed down based on the color. And you can detect that by putting it into a spectrometer with the pump on and with the pump off. The interference part comes into play because there's a reference beam. So we basically copy the probe before it interacts with the material, and then interfere it with that afterwards to see to see the phase delay, so how the index of refraction changed for different colors. Importantly, the probe and the reference are what we call chirped, which means as they went through different glasses, the different colors got slowed down different amounts. So the red is actually like closer to the front and the blue is in the back. The reason that matters is because we have very precise control over the time delay between the pump and the probe. So essentially, we can scan the pump across the probe and pick which combinations of colors are interacting with the material. They go through that microscope objective you saw. They get focused onto the sample. The probe is modulated by the excited state of the material. They come out, they're interfered, going to an imaging spectrometer. And then from that interference data that we collect, we can figure out the phase delay, so the change in index of refraction, and the amplitude of the intensity, so how much was absorbed. For you to get a context of what that looks like, this is a picture of me playing with an interferometer on the table to maximize the interference fringes, which is the orange data on the back. If we were to zoom in on that, an example interferogram looks like this. So it's something, we usually think of interference in a spatial domain, and this is in the frequency domain, so like we're interfering with wavelength. And if we did a Fourier transform on this, and for several different time delays, so several different overlapping photon energies, we could figure out what the phase delay was for each of those. So what you're seeing with the straight line is the pump is being swept across the probe, the chirped probe. So each peak is a different combination of photon energies, and it's showing the amplitude is the change in the phase. We construct one of those for the phase and the amplitude to extract these two properties of the optical effects of the material. I've been talking about these optical properties for a while, so to properly introduce them, they're not very complicated. N2 is an optical Kerr effect. So essentially, we all know that index of refraction changes with the energy of the light, so like the wavelength, but it also changes with intensity. If we have a first order approximation, so assuming it's linear, N2 is the slope. It's a 2 because electric field intensity is E squared. So beta is similar, but if we take alpha to be the absorption, it's the 2 photon absorption, but that's the slope with intensity. And this graph is just showing you that 2 different colors can excite the valence electron using a phonon or not if their summation adds up to enough. Okay. And so now we're moving on to the final slide, which is the data I collected. Something that we're doing that's special with this experiment that we're doing is that we're using a reference material to try to precisely measure this. So currently, we're using fused silica, which is a sort of glass, to normalize our data. And we could talk about this data, but what I want you to understand about where we are right now is that this is the first step, and at the end, we want to have a simple way of having, for any combination of photon energies, what the N2 and beta are for a material. This is only 2 probe wavelengths. Ideally, we'd have axis of wavelength, and a color or intensity would show you what the numbers are, so that for any experimental setup that you have that has multiple photon energies, you could figure out what these numbers should be for that material. So that's what I did this summer. Thank you.
Awesome job, fantastic. So questions?
If your reference and probe beams have multiple wavelengths of light, how did you interfere those?
Well, okay, so the table's kind of complicated. There's two Michelson interferometers, and so essentially the first one splits a probe. The probe is generated by the water cell, so then we have like this weird spectrum, and it splits in this 2. And then later they get recombined after the probe gets messed up by the state of the material, and then they get physically recombined. Like they start propagating together, and they enter a spectrometer. And so usually when you think of interference, you think of fringes, but what's happening in a spectrometer is these 2 beams together are going to be diffracted, they're going to be in an array based on color, and then each color is detected. So they're interfering when they're diffracted like that.
Okay, thanks.
Question in the back?
I have 2 very dumb questions. So, first of all, as somebody who has spent 3 hours trying to align a laser with a single pinhole, how long did it take to get that optical table set up? And what happens if you just sort of bump into it? Do you have to recalibrate everything, or what's the deal there?
So there's multiple experiments happening on this table simultaneously.
I would imagine
So what happened is when I came, they were doing another project, and this one was kind of the experiment was pretty well situated that we could convert it into something else. And it's honestly a lot more robust than I've ever experienced any optics being before in my entire life. I don't know if that's just because Jared was better at telling you how to fix things, or if it was because it was actually more robust. But it was the easiest optics I've had in a long time. It would take about, if we wanted to convert one experiment to the other, it would take about 2 hours of aligning stuff.
And then just as a quick follow-up, what's one thing you learned from your summer experience?
Oh, geez. And I should have thought you were going to ask that. I guess imaging is a lot more complicated than I thought it was. And the mathematics of interference was also a lot more complicated than I thought it was. Not that I thought it was easy, but not that I ever thought about it.
All right, well, hello, I'm Emma Goulet. I'm the Center for History of Physics in the Niels Bohr Library and Archives intern. And this summer I spent my time researching underrepresented women in physics. So I'm sure most of the people here know of the general trends and statistics of women in the field. It's pretty much that women are staggeringly less likely to join the field in the first place, and once they're in, they report slower career progression than men and are more likely to prioritize family over physics. And these are kind of the general trends that set the expectations for women in the field. And so how can we increase diversity in the field? Here you go. So in order to increase diversity, one way that I focused on was increasing the amount of role models that we see. So when women see more women in the field, they can feel more comfortable and more inspired to join. And I think this is particularly important for kids to see as well, so that they can see that they're represented and they can have someone to look up to. So this summer, I set out on a mission with the CHP and the NBLA to kind of research 2 important women in the field, Catherine Clerk-Maxwell and Emily Du Châtelet. And then I created teaching guides on them for grades kindergarten through 5th grade for kids to kind of be able to learn this as early as possible, see that there are women in the field. And then I made a bunch of different outreach articles for older audiences and for adults, and just more general public to learn about these women. And I wrote a couple of different articles for AIP, an APS essay. I updated the women's Wikipedia pages, which were pretty lacking, and I'll take more information to them to 2 different conferences in January. So first, to start with Catherine Clerk-Maxwell, Most people here probably recognize her name through her husband, James Clerk Maxwell. He made a lot of notable discoveries on things like electromagnetics. He did a lot on the viscosity of gases. And I'm sure most of the interns here will know him most for his work on Maxwell's equations. I'm sure that's a pretty recognizable name. But what a lot of people don't know is that Catherine was behind a lot of his experiences working as kind of this skilled technician and research subject. And so Catherine is kind of this example of a partner and a spouse to a really prominent physicist whose work is both pretty much completely undocumented, and she doesn't have any credit at all for the work that she did. And this is what I wrote a lot of my outreach on with her. Stephen Chapin is a really prominent sociologist, and he credited this term invisible technician for people in this position, that they end up doing a lot of the skilled work for science, but they don't have a hand in as much of the math or theoretical components, so they don't receive any credit for it. So this is an example of the kind of research that I did. This is on James's work on color theory, and as you can see, I did archival research. So this was going through a lot of primary sources, and this was I was basically reading through all of James's recorded personal correspondence and postcards with close friends and family to see pretty much just whenever he mentioned his wife. Any mentions of his wife and his super personal correspondence, I was picking through it. So this is an example of his paper on color theory. And as you can see, he labels an observer J. He specifically names that as himself. But then there's a second mysterious observer K, which is completely uncredited. And this is later confirmed to be Catherine through a letter between James and one of his friends that he sent out 2 weeks after this paper. And this is another example of some of the research that I did. This is on James's work on the kinetic theory of gases. And on the left is a postcard with one of his close friends that mentions that Catherine, his better half, his wife, did a lot of his work, or the theory behind his work. And then on the right, his biography later confirms it as well, which was written by 2 of his close friends who also mentioned that Catherine did a lot of work for this. And this kind of brings it back to the question of credibility, because it says on the right, she did very exhausting manual work because she had to maintain fires for several hours and days at a time in order to study these gases. But she didn't do the math as much, as far as we know, so she wasn't credited with anything. So moving swiftly along to Emily du Châtelet, she was an absolutely incredible figure in 1700s France. She did a lot of philosophy, she was a physicist, she was a mathematician, she was a translator. She was absolutely amazing. Some of her most notable work is on the physics of heat transfer, which was published anonymously, so not with a woman's name in 1700s, but it was published alongside some of Voltaire's work and some of Euler's work, just to name a few of the people that she was around. She did a lot of work on foundations of physics, combining different philosophies of physics together. And her most capstone work was that she translated Newton's entire Principia. And this, if people don't know what this is, it's pretty much the physics book. It was Newton's work on forces of motion, on gravity. It was absolutely huge, and this was originally written in Latin, and she translated it into French. And this was a huge advancement for the time because science was not very accessible. So her translating this massive work from Latin into French was a massive advancement. And she not only translated it, but she also annotated it, she added her own explanations, and she did huge things for making it accessible. And she did it all while she was pregnant. I'm just going to mention that. She sped through it in that entire time. And it's still the standard translation that's used today from 1700s. So she was actually pretty well respected for being a woman that was educated at the time, even if she couldn't formally receive her own education, which is why it's super disappointing that history pretty much remembers her first for being Voltaire's lover. She did have a long-standing affair with Voltaire as they worked on a ton of philosophy and physics and just science projects. But because of her role as a woman in history, she's remembered most for her relationship with Voltaire. If you Google her, that's what comes up first, not her whole translation and all this amazing stuff that she did. So Emily she's pretty amazing. She's a pretty amazing, inspiring figure. And as you can see, she's super outspoken for all of women's rights, for her own education. She actually, one of my favorite stories about her is that she would literally dress as a man to get into some of these French thinking cafes and just learn as much as she could. For a time, her house was the biggest library in Paris because she was trying to learn as much as she could, and she was taking any avenues that she could to do it as a woman in France. And it is a real shame that she's kind of thought of as Voltaire's mistress instead of for her own intellect, despite her multiple publications. And this is pretty much what I wrote my outreach article for her about as well. I wrote about the misrepresentation of women in media, how this does often happen, especially to women in STEM. So thank you so much. Thank you for listening. And I wanted to say thank you to my mentors because I didn't know how to do history research, and it's pretty tedious going through all of someone's correspondence, and you can find all my work and everything down at the right.
Great job.
Thank you.
Question?
First off, I love that Brad's name is in Comic Sans.
It's tradition.
Second, what did you find most interesting about any of the research process?
Ooh. So the research process was actually, well, I can show you. I brought this. This is pretty much, I have 3 of these and many other books. This is just James's personal correspondence. When I say that I was going through all of his personal letters to try to find any mention of his wife, I mean it. That is what this kind of research was. And I thought, honestly, the most interesting thing was just learning how to do history research and archival research, because it's a little tedious, but it was really fun being able to find, like, ooh, he mentioned his wife. What's she doing at the time?
Question? Between Catherine Clark Maxwell and Emily Duchâtelet, are there any really interesting favorite facts that you learned?
So with Catherine, it is, unfortunately, we have extremely little records of her. Like, when I say we have little, I mean it's pretty much only in James's correspondence. But I actually have another. So these are my mentors, first of all, and some of my outreach. But on the right, that's Catherine James and their dog, Toby. The dog comes up a lot. The dog comes up all the time, always. And that's because it's confirmed at least 4 dogs that were the same kind of dog had the same name. So his friend wrote this quote that I love that says their dogs lived in hereditary succession. Like Toby lived for years and years and years because there was 4 Tobys minimum. We don't know how many there were.
Real quick. Okay, something that I was wondering is in reading his correspondences and only finding her information through him, I was wondering if obviously she didn't have any publications or anything, how did you feel his relationship, his respect towards his wife was in the scientific domain?
It was actually, I wouldn't think that it was really great, but their relationship was really sweet. He wrote a lot of love letters and poems and everything about him. They greatly, greatly respected each other. And she was kind of serving as this subject of experiments, like in color theory. She would try to match colors and kind of help be a second pair of eyes. Or for his other experiments, he was kind of doing skilled work because they were working out of their home. But he seemed really appreciative of it and their work, which is nice to hear, but then she didn't get credit.
Hi everyone, I'm Janessa. I am the SOC intern, and I couldn't have done the work that I did this summer without the help of Brad Conrad and Michaela Cleaver. Like I said, I'm Janessa Sloan. I'm a senior at Embry-Riddle Aeronautical University, majoring in space physics with a minor in computer science. I was previously funded by Arizona NASA Space Grant for my work on new short-range tests of gravity. Not only am I the SOC intern, I am also an SPS AZC, which is an associate zone counselor representing Zone 16, and I am also my chapter's president and have been for 2 terms. This summer I worked on outreach and engagement. I worked on outreach and promoted outreach to over 800 chapters around the world, and I promoted outreach to the general public and younger generations by working on things like Astronomy on the Mall, which is a 50,000 person event literally on the National Mall, adding videos to the demonstration library, and creating a new Physics Jeopardy, which is now called Physics and Astronomy Jeopardy. And of course, I worked on my SOC, which is the Science Outreach Catalyst Kit, and I will talk a little bit more about that later on. First up is Astronomy on the Mall. The image on the left is a couple of the interns interacting with the general public at the Boomwhacker table, and I really enjoy this picture because the Capitol is in the background. Like I said, we were literally on the mall. A lot of things went on behind the scenes in Astronomy on the Mall. There was a lot of planning, organizing, and presenting. So I actually was able to choose all of the demos that we took. This involved me picking which ones would be most beneficial for the younger generation and the general public, which ones would be suitable, and which led me to develop and test and order all materials for each demo. And then our one job was presenting. So I had all of the interns help me out, and some of them brought all of the demos to the mall for me, and I think it was a very rewarding experience to share our passion for physics and astronomy with future generations. So here's an image of a couple of us at the electromagnet and Boomwhacker table, and these are all of the demos that we took. Next up is the demonstration library. The image to the left is me performing the Cloud in a Bottle demo, and some may say this is my favorite. So I added 7 new demos to the SPS demonstration library. You can view all of these videos either on the SPS National website, Instagram, TikTok, or even YouTube. So here are some images of all of the demos that I performed. You can perform them yourself just by watching the tutorials. So to promote outreach throughout the school year, I have multiple videos scheduled to release on YouTube and Instagram and TikTok throughout the rest of the year. And as Brad Conrad once said, demos are cool. Videos of demos are even cooler. Next up is Physics and Astronomy Jeopardy. The gift to the left is me and my chapter actually playing Physics Jeopardy last year, and someone screamed vectors, and I'm pretty sure that was not the answer. So like I said, we are surrounding this around the astronomy theme and changing the name, so we have all revamped questions that surround that astronomy theme and new categories. The only category that remains the same is alphabet soup, which is the one where you have to guess the acronym, what the acronym stands for. So the new categories include equations, planets and stars, relativity, general, and miscellaneous. So as a quick example, for planets and stars for 200 and this amazing spherical cow, does anyone know the condition when 3 celestial bodies are arranged in a straight line? If you're in my practice group, please don't answer. Does anyone know? If you were in my practice group, you can also answer now. Valeria? A syzygy? It is a syzygy. Good job. Congrats. I'm going to give this to you real quick. Okay, running back. Perfect. And then last but not least is my SOC. SOC stands for Science Outreach Catalyst Kit. The purpose of the SOC is to provide a kit of demos and activities to at least 80 chapters around the nation. And all of these demos and activities surround one theme, and this year the theme is eclipses. So to the left is the SOC design that I came up with this year, and it actually, coming over here, it actually closes all of the boxes. So we designed it for the tape to secure all of the boxes to ship out. Next up is my SOC timeline. This is a rough timeline, but during weeks 1 and 2, I was brainstorming the SOC theme ideas. I kind of already knew that I wanted to do something surrounding astronomy and eclipses, so I chose eclipses. And weeks 3 and 4, I started to build that plan for the eclipses, which involved picking which demos would benefit the chapters more and what can fit in the box. Moving on to weeks 5 and 6, I ordered all of the materials, wrote all of the instruction guides, had them edited, looked over, and I laminated a lot of them. And then if you saw my desk during weeks 7 through 9, you know that I was packing the boxes. Do I have to hold this still so I can show? Do I have to hold this? Can you hold it? Okay, moving on to components of the sock. The first component is the wooden orbital model, which is the centerpiece of the sock. It is this right here, and it's a little toy that is actually powered, and it moves around to show orbits. And then the Scale the Solar System demo, which includes receipt paper in the sock so that chapters can scale the solar system down to 1 meter, 2 meters, 3 meters, with conversions included. We have the paper model demo, which is intended for younger kids so that they can visualize a lunar and a solar eclipse. We also have brass brads so that they can make these themselves. And what's unique about this year's sock is the box is actually a demo as well. So this year I added cut here stickers on the side of the box so that they can make their own pinhole viewer so that they can view the solar eclipse safely. And then of course there's a thumb drive with all the presentation guides and paper model templates, safety guides, stuff like that. A huge thank you to Brad Conrad, to Michaela Cleaver, to Kayla Stevens, and to Andrew back there for everything, and the SPS team, and all of the interns for making this summer very memorable. Thank you. Thank you, thank you.
Questions from the audience? Ben.
I have a question about your socks. What is your favorite part of the kit?
Wow, that's a great question. I love the whole thing. I would say my favorite part is definitely the toy model because it's a beautiful centerpiece. I don't think we've done anything like this in the past. But I really enjoy every single demo that's in this kit, and I really enjoy that the box is also a kit. So yeah, I think that's, yeah.
When's the next big eclipse?
It's 2023 and 2024.
What's your biggest takeaway from being the sock intern?
In terms of work or in terms of, in what terms?
Whatever terms you want.
Okay. I would say my biggest takeaway is probably just having creative freedom. And I think Brad and Michaela really let me have that this summer. I now realize that that's really important to me. I designed pretty much the whole box by myself with some approval. But yeah, I think creative freedom is the biggest takeaway. Yes.
Last question in the back.
So why was the bottle your favorite demo? You said in the video the clouded bottle was your
The cloud in a bottle. I actually don't think that's my favorite, but a lot of people do think it's my favorite because I was talking about it a lot. But it's a really amazing demo, and it takes less than a minute. You just use isopropyl alcohol, a bottle, and some pressure, some air pressure. But yeah.
Round of applause.
All right, hello everyone, welcome, and thank you for coming today. My name is Ben Johnson. I'm a student at the University of Virginia studying physics, and this summer I worked at a company called Potomac Research down in Alexandria, Virginia, and I was studying a type of machine learning called reservoir computing. And before I go any further, I'd just like to thank my mentors and the team at SPS for all the help and support they gave us this summer. All right, so to start off, I'm going to go over some of the main goals that I had or that I was working towards this summer. The most general overarching goal was to use this type of machine learning called reservoir computing to model or to solve differential equations that model certain physical systems. And since differential equations pop up all throughout the fields of science, this type of research has very broad potential applications. The second main goal was to implement a specific type of reservoir computer with a hybrid characteristic, meaning that it was part machine learning and also part numerical method calculations that would help the machine learning along. And the final way was to experiment with some different various ways to train the reservoir computer. And unfortunately, due to time restraints, I'm not really going to be able to talk about the second two goals all that much. So this talk is going to serve as more of an introduction to reservoir computing. All right, now let's go over the basics of a neural network. The neural network is a computational architecture inspired by the function of the brain. So I'm guessing most of you are, at least to some extent, familiar with the functional unit of the brain, the neuron. Now these are cells that are connected to each other, and they can achieve a level of excitation or activation, causing them to fire. And that passes that signal on to the other neurons surrounding them that they're connected to. And those in turn can become activated and fire as well, carrying on that signal. And that is the basic premise of a computational neural network as well. So in a computational neural network, we have the same subunits called neurons, but rather than the more binary biological case where they either fire or don't fire, we have a certain level of activation, which can be thought of as more of a percentage. So each neuron at any given time has an activation level between 0 and 100%. Now, if we look at this left diagram up here, this is a relatively simple version of a neural network called a feed-forward neural network. And in that diagram, all of the circles represent neurons in the network. We start with inputs, an input layer, and that passes the activation from left to right in one direction, like the boy band. Well, former boy band, I should say. And each layer passes on that activation level to the next layer in that sequential order. Now, this is distinct from a recurrent neural network over here on the right, because in a recurrent neural network, the neurons have the ability to pass back to previous layers. So that's what the arrows on the top and bottom represent. So this makes training them quite a bit more complicated, but it comes along with certain advantages. One of the main advantages is memory. So for a task like image processing, a feed-forward neural network is very much sufficient. It doesn't need to be able to remember anything to analyze the photo, because all the information is present in the photo at the same time. But if you're doing something like speech processing, in order for the computer to be able to make heads or tails of a sentence, it needs to be able to remember the beginning of that sentence by the time it gets to the end. So the point is, for certain tasks, a recurrent neural network is advantageous to use, even though they are more difficult to train. And that is where we come to the reservoir computer. So a reservoir computer is a type of recurrent neural network with the distinct advantage of being much, much easier to train than most other recurrent neural networks. So we can understand the function of a reservoir computer from this diagram down here. If you look in the middle, this big bowl of spaghetti and meatballs represents the neural network. You can think of that like the recurrent neural network slide or a diagram on the previous slide. And we start with our raw input data, represented by these squiggly lines here. And in my case, remember I said I was working on differential equations. So for us, the raw input data was certain sample solutions to those differential equations at certain parameter values and with given initial conditions. So our output that we desired was to get a new solution, a prediction of the solution to that same equation, but with different parameter values. So the idea was to train the reservoir computer on that sample at certain parameter values and get it to predict new ones that it hadn't yet seen. And so we start with our input data on the left there, and it's passed into the reservoir by using something called an input weight matrix, which is represented by this blue rectangle here. And that is a matrix in the linear algebra sense. It's a 2D array of numbers. And it has an associated function for converting raw data into initial activation states within the neural network. So after giving it some time to analyze and train on that data, we can ask for a prediction of the equation with a new parameter value. And to do that, we pass the activation states in the reservoir back out through an output weight matrix. Again, just another linear algebra matrix. But this is a very important one because it's converting from the activation states in the reservoir to the final output data. So it's key to get this right in order to get the desired outputs that are actually useful. And so this is where we come to the main advantage of a reservoir computer over other types of recurrent neural network. So in most recurrent neural networks, you need to train the input weight matrix here, the weights of the connections between the neurons within the network, how strongly they communicate with each other, how well they pass activation. And then you also need to train the W-out matrix. In a reservoir computer, you only need to train the output weight matrix. So it's much easier to do. And I'm going to finish off by talking about a few of the equations that I worked on this summer. The first here is the van der Pol equation, which models the van der Pol oscillator. This is found in the field of electronic circuitry, so it is somewhat useful. And what's interesting about this equation is due to its nonlinearity, you see the x squared term in the equation up there. You can't actually write down an explicit closed form solution to this. You need to solve it numerically. So you have to use a computer to get a good answer, essentially. Now you can see on these graphs the prediction from the reservoir computer. If you look carefully, there are actually two colors. There's blue and red. The blue is an integrator's prediction for the equation to very high accuracy. And then the red is the prediction coming out of the reservoir computer. So you can see they're lined up very well. It's pretty accurate. Now, the point of this equation was to start with something relatively simple. Although it is nonlinear, it's not incredibly difficult to model. So we wanted to start with a relatively simple equation before moving on to more complicated systems where a reservoir computer would actually be more advantageous in the future. So this is the next system of equations that I worked on called the Lorentz system. And this one is a bit more interesting and a bit more difficult to work with because for one thing, we have three coupled nonlinear equations, and they also exhibit chaotic behavior. So actually, the man Edward Norton Lorenz, no relation to the guy from Fight Club, came up with the phrase butterfly effect. I'm guessing even if you're not familiar with chaotic systems, you've probably heard of that. The idea is if you adjust or perturb the system slightly, you can end up with a very different trajectory. So these are inherently difficult to model because if your model gets off just a tiny bit, then in the future it will just continue to diverge from the correct prediction. So I spent a good bit of time working on this, and you can see, like I said, it does diverge eventually, but we were able to model it for some time, and we will hopefully be able to move on to more complicated systems in the future. Now, that is it for me, so thank you everybody for listening. If you have any questions, feel free to ask.
Questions from the audience?
So you've been testing your reservoir computer against an innovator, right? An innovator would be like a brute force method. So what I was wondering is after you train your neural networks, like how much computational time is the contrast?
How much time to do what? To predict for the equation?
Yeah.
It's pretty quick to predict. So a lot of the time was training. So for example, if I wanted to train over, let's say the Vanderpool, it had that one parameter mu. We could train from like mu equals 0 to 100 by doing, integer values like mu equals 1, 2, 3, and so on. So that would take much longer because we would have to run the reservoir for that. But then to actually predict for, say, mu equals, 50.5, it would be rather quick, like less than a minute.
Great question.
So what hardware and what machine learning model or libraries did you use, and what was the size of your data set?
So I did all this in Python, and we used a module that was actually developed by the people I was working with. They called it ResPy, so Reservoir Computing for Python. And the hardware I used was just my laptop. I used the Spider IDE. So that's one of the big advantages of this type of machine learning. Systems that are like this Navier-Stokes system is very complicated, and to predict that accurately right now, people use like supercomputers that are time and energy inefficient, but I can run this on my laptop, and in the future you could maybe predict systems like that with a reservoir computing system, just on a laptop that is much cheaper and faster to run. Does that answer your question?
What did the day-to-day look like while you were working on this?
So actually most of the summer I spent on the third goal that I had on the right, which was experimenting with different ways to train the reservoir computer. So I didn't really understand any of this stuff terribly well when I came in, so it was kind of a lot of guess and check, just try different things and see what worked. But yeah, I was mainly working on getting the reservoir computer to accurately predict the systems using different training methods. So I'm sitting at a desk coding.
Round of applause, great job.
All right, thank you everyone. I hope you had a chance to stretch your legs. I'm Nicole Liang. I'm the SPS NASA intern. My mentor Eric Switzer works at the Goddard Space Flight Center up in Greenbelt. And today I'll be talking about my work with the Exclaim star camera system. So before I jump in, what is Exclaim? Exclaim stands for the Experiment for Cryogenic Large Aperture Intensity Mapping. And it's a balloon mission that will carry a telescope and spectrometer up into the upper atmosphere. And its goal is to map carbon monoxide and carbon ion emission in the early universe. And it's special because the spectrometer is really small. Normally they're very big and clunky, and it has to be cooled down to less than 100 millikelvin in order to work properly. So here's a picture of the spectrometer. That is the thing that has to be cooled down that much. The spectrometer goes into the receiver along with a bunch of telescope hardware, and that receiver is placed in this cryogenic dewar, which is cooled down with liquid helium. And this dewar goes onto the gondola frame, which is connected to the balloon up top. So one important thing for this mission is for the telescope to know where it's pointing all the time. And I worked on the star camera system, which is a key component of the system that helps the telescope do that. So the star camera is something that many spacecraft use in flight to keep track of their orientation. And our camera in particular it has a very high resolution, which is so high that we can tell where the telescope is pointing within a margin of 1 arcsecond, or 1/3600th of a degree. So the star camera is part of the Exclaim Attitude Determination and Control System, which is essentially this group of instruments that helps the balloon know how it's oriented in the space it occupies. So the way the star camera works is it collects pictures, it figures out what stars it can see, and then it matches those stars to stars in a database. And from there, once the camera does that, it can talk to other instruments in ADCS. In particular, the star camera helps to calibrate the magnetometer. So I had 3 goals for this project, split roughly into thirds in the internship. So the first goal was to get the software to analyze any picture of the stars. The second goal was to get the camera to take a picture of the stars. And the third goal was for me to design a mount system for the camera so we could test it in the field. So I'm going to talk about software that goes into the camera. So our camera is an IDS micro eye camera that comes with its own software suite. It is normally used through the computer graphical interface, but while the balloon flies, no one can operate it because the gondola is in the air. So we need a program that will run in the back end to tell the camera when we want to collect images and to trigger the camera automatically. So this program is written in C, which is a computer language, but we want our programs for the gondola to be written in Python. So we can interface with it with a Python package called PyUI, but it has 0 intelligence, and there's an absurd amount of camera options. So to make things easier to use, I developed a class wrapper to encapsulate all the functions that we need to get the camera to take a picture. Next up is the lens controller. We use the Berger Canon EF lens controller to control our 200mm Canon lens. And we need it because while the balloon is flying, it's very cold up there, and there's very small temperature changes that deform the shape of the lens, enough so that we need something to adjust the lens aperture and focus automatically. And finally, we have the image analysis program, Astrometry. Some of you may have used this before. It's a very powerful online web service that can also be downloaded as a software package. And what it does is it looks at a picture and it figures out what stars are there just by looking at the pixels in the picture. So I downloaded this package. It turns out you can only interact with the functions through the command line. So again, I made it easier to use by developing an image analysis program in Python that could interface with the command line through a Python package called subprocess. So before I go any further, I want to explain where the software is on the camera. So on the very left, we have the camera driver, which controls the imaging sensor. The imaging sensor is connected to the lens controller, which controls the resolution of the picture that comes out by adjusting the telescope or the lens. From there, that picture is sent back to the flight computer so that the picture can be run through the image analysis program. The camera cannot analyze pictures by itself. We need the computer for that. So here's an example of what the software can do. Can we get the lights? Or I can get the lights, or you can get the lights. It's all good. So even with the lights off, it's pretty hard to see the stars. They're there. They're like in the middle of the picture. This is what the software can see. So you might notice there's some red circles in the middle. Those red circles represent what stars the program saw from the picture. And the green circles are stars that the program filled in by cross-correlating with its database. And the way it did that is it took these stars in groups of 3 or 4 and compared them with groups of 3 or 4 stars in the star catalog to form a match. And so that's what that triangle is in the middle. And so here, these are constellations that the program was able to match with the star field image. All right, we're going to shift gears a bit, and now I'm going to talk about hardware. So I have never worked with hardware in a research setting before, so this part of the project was really exciting for me. So this is the star camera mount that I designed for the balloon. I designed it in SolidWorks, which is an industry standard mechanical design program. So that circle thing in the middle, that is a dummy model of the camera, and we had to design the mount around it. So the biggest challenges in designing this are that, first of all, we had to get everything to fit. So it's not on the design right now, but we have to put more hardware and electronics and wiring around the camera to get it to work. So I designed the mount to take up as little space and be as light as possible without sacrificing its mechanical integrity. The other thing we need to do is minimize the time and cost of machining this mount. So it's very expensive and time-consuming to design custom parts. So what I did is I went onto our mechanical part vendor's website. Our vendor's called McMaster-Carr, and I looked at standard size mechanical parts. So for example, this L channel right here, it has a thickness of 1/8 of an inch, and it's 2 inches long on either side, and that is a standard size for an L channel on the vendor website. So here, this is the star camera in the lab, and I just want to point out some more hardware that doesn't have software attached to it. So over here, we have the lens holder, and what it does is it attaches the camera to the mount very securely. And up on top, we have the baffle. And when the camera is mounted on the gondola, that baffle will be replaced with a big encasing shell that will encase the whole mount. And what it does is it stops stray light from hitting the camera lens. The camera itself is about 1 foot long. Like if you hold up your forearm, it's about that long. And if you make like an O shape with your hands, that's about how wide it is. And it weighs about 5 pounds. The picture on the right is a picture of the power supply connection for the camera. So Eric and I, we had to test the pinout of the connector to figure out which one was ground and power and whatnot. And once we found it, we soldered the connection to the camera and we covered it with an insulating wrap. So what comes next for the star camera? We need to integrate it with the rest of ADCS. So that would mean we need to make sure it can talk to the flight computer, that it can receive and send messages. We also need to build the camera and attach them to the mount and take it out for a test flight in the fall of 2022. For Exclaim will launch in the fall of 2023, and if it's successful, then spectrometer technology that we developed will be used in future spaceflight missions. So that is all I had for today. Thank you again so much for listening. Does anyone have questions?
Okay, good question.
What, if you know, what material is the balloon made of?
That's actually a really good question. I'm not sure what the balloon material is made out of, but the balloon actually looks like a hot air balloon, like in a cartoon.
Good question.
How high up does it go?
It goes up into the atmosphere, I would say about 10,000 feet, 10,000 feet.
So like 2 miles?
Yeah, 2 miles.
Really high.
Really high. Yeah.
Okay. Round of applause.
Hello everyone, my name is Anthony Olguin and I am a senior at the University of Maryland in College Park, and I am currently double majoring in physics and astronomy, and this summer I was the Space Telescope Science Institute research intern. And this summer I was looking at studying galaxy formation via nearby star-forming galaxies. So the first question you might be asking is, why study these star-forming galaxies? Well, it helps to understand the evolution of these current galaxies, and it can also tell us about the formation of new galaxies that could be coming around. So it lets us look into the future and the past of anything that's here, or if we wanted to make our own simulations of anything. One way we can do that is the way that we do it is by looking at the looking at the properties of ionized gas via emission lines. And to do that, my research this summer had 2 parts. It was compiling tables with these properties of ionized gas through different literature and looking at a bunch of different galaxies, not just the one that I analyzed. And then I created a data cube of NGC 4449, which is here on the right. This image was taken through the Hubble Space Telescope, but the image that I looked at and analyzed was taken from the Gemini North Telescope. So there are two Gemini telescopes, Gemini North, which is in the northern hemisphere and is the one that I will be talking about, and Gemini South, which is obviously in the southern hemisphere, so that way we can get two different views of the night sky. The North Telescope is located in Hawaii, and the instrument that was used to collect this data is the Gemini Multi-Object Spectrograph. This spectrograph operates in two different modes. There's single slit, which has a smaller field of view but has an extended wavelength coverage, while the double slit mode has a wider field of view but a more limited wavelength coverage. And the Gemini North Telescope used the single slit for this analysis of NGC 4449. And this image on the right was taken by Joe Pollard, and this is an image of the Gemini North Telescope, a time lapse of about an hour, so that way you can see the cool little star streaks that you see right there. Next one. So to do this, we need to do an integral field spectroscopy data reduction, or IFS. And what does IFS do? It provides spatially resolved spectroscopy of an object over the entire field of view in a single exposure. And there are three different techniques that an integral field unit can use. There is the lenslets and fibers, and the slicer technique. The Gemini North Telescope uses the lenslets and fibers technique right here, and the fibers take the light from the different parts of the detected object, transfers them to the slits, which then goes into which makes the spectrum over here. And the result is a three-dimensional data cube that has X and Y and wavelength coordinates, which I will show you in the next couple slides. But before I can show you the data cube, you have to know about the reduction process. First, on the right here is the actual raw calibration data that I looked at and collected, which is the twilight and calibration flat, the copper argon arc lamp, and the standard star that we use for flux calibration. First, you reduce the calibration flat, and while we're doing that, you look at the 750 different fibers that are on the lenslet and fiber integral field unit, and you make sure that they're all matched. So they're coming groups of about 50, and you look at one, and they're numbered 1 through 51, and you make sure that they're actually in order, because if they're mismatched in any way, you won't even notice, you won't see it until after you make the data cube, and then you'll have a messed up image. And once you do that to the calibration flat, you can apply that to or you can extract the spectra, and then from each of the fibers, and you can then do that to the twilight flat and reduce that one. And then next is the wavelength calibration, which you look at the copper argon arc lamp from the spectrograph, and then you compare the wavelengths from that data collection to some known emission lines. So you can use the NASA database or the NIST one. And then once you figure out what the discrepancies between the wavelengths are there, you can move on to the standard star and reduce that in order to do the flux calibration. And then once you do all of that, you can now apply all of these different calibrations from the raw data and apply it to your science object, which then creates the three-dimensional data cube of NGC 4449. So on the right here is my data cube that I created of this galaxy. And the one on the far right over here is at the 4,860 angstroms, which is the H beta emission line. And then over here is O3 at 5,007. And these little green squares are just the regions that I selected for the program that I was using to take the spectrum of. And each slice is of a different wavelength. So you're looking at the exact same image of NGC 4449, but you're looking at different wavelengths. And the brightness, so there being brightness here indicates that there's an element at the element at that wavelength located here. So if it was dark, if you didn't see anything, that means at that wavelength, whatever is there, it isn't there. Next one. So here is the emission spectrum of NGC 4449, and the blue lines here are the principal emission lines plotted on top of their rest wavelength. The ones that are most prominent are the O3 at 5,010, and then the O3 doublet at 4,962, the H beta at 4,865, and then helium-1 over here at 5,880. So the information that you can get by looking at these emission spectrum is the type of star formation going on in the galaxies, the temperature of the galaxy, the density, and the chemical composition, the makeup and what's going on inside, which is pretty important. So this is the second part of my project, which was creating these data tables. So I collected information from over 25 plus papers, and all of them included different galaxies, and it talked about different parts like the equivalent width of lines such as C3, C4, and O3. It also had their gas phase metallicity and their different types of element ratios. So for instance, I looked at one with carbon to oxygen ratio. Others had nitrogen to oxygen, oxygen to hydrogen, which is the gas phase. And I also recorded the range of redshift values of Z from 0.003 to less than 9. So here is a graph of one of the tables that I created. And this one is on the X, the gas phase metallicity, and on the Y, the carbon to oxygen ratio. And you can see that there is a flat trend about from 6 to 7.5, and then you can see a steady increase here from 7.5 to 9. And so all these different data points are different objects that you can see in the sky. So these blue ones here were for Berg 2016. Those are actual galaxies, while the rest are different types of stars. So some are stars seen in the Milky Way, some are DLAs, halo stars. So this way, what we're trying to do is show that the origin of carbon, so ones that have lower metallicity, that might be younger, have a flat trend, have an X amount, and it stays pretty flat there. I don't know if you guys, there it is. And then if you look at from 7, which are these older ones or newer ones that might have more metals in them, they have an increasing trend. So those you can, so that's part of the different things you're trying to look at when you're putting these tables together. So in summary, I had two parts of it, the data reduction and making these tables. And as again, so future works these can be applied to is looking at other works, or I can, if I wanted to look at different galaxies, I can use the tables that I put together, so that way I'm not just looking at one that I made this data cube for and then another. And it can help determine, like you can use this information to help determine the gas phase metallicity of an object, or how new galaxies can form in certain conditions, or evolve over time, as mentioned before. So I just want to say thank you to everyone at SPS for putting this program together. I really appreciate it. It's been an amazing summer. I want to thank my mentor, Dr. Namisha Kumari, and I want to thank all of the other interns for making this such an amazing summer. It was great getting to know all of you. Thank you.
Questions from the audience?
What program did you use, and did you have any difficulties with the program?
So I had to use Linux. I had to download Linux on my computer when I first got there, because apparently that's what you have to use it for. So I used the the Gemini IRAF data pipeline, which that one has to use Linux in order to properly use it. So I had to learn how to overcome this learning curve of using Linux for the first time. I haven't actually used that system before, and it took a few weeks it took 1 week to just figure out how to do it and how to download it without having to partition your drive and do all this crazy stuff that's not fun. And then the rest of it was done in Python and DS9. So the images I created previously, these are all done in DS9 here. Yeah.
Okay. Real quick one.
What was your favorite part of this project?
My favorite part was creating this data cube. So I wish I could have made a GIF or some type of video to show it better. But like I said, each different slice is a new wavelength. So I had 6,000 some odd different wavelengths that I looked at. And there's 6,000 different images of these. So each one, and you can make a video of it showing the different elements as the flux goes up and down, and you can see the different elements that are there in that galaxy. It's really, really cool to watch the video. So that was my favorite.
Round of applause for our speaker.
Hello, everyone. Thank you for being with us today. I'm Gesam Dong. I'm from Bowdoin College. I'm a rising junior. I'm pursuing a bachelor's in physics and government and legal studies. And over the summer, I worked at ACP as the SPS science writing intern for Physics Today. And consequently, I'm going to be talking about science writing and installing confidence into writing today. So I'm looking around the room. We're mostly physicists here, so there's no shame in making confessions. Well, one that I'd make about our own kind is that explaining our life's work is not exactly our forte. Although I'd say my fellow interns all proved me wrong before. Well, that's exactly why we need science writing. It is just easier to understand for many demographics with different backgrounds than just going online and finding a scientific research paper. It is compact and concise. It delivers just the right amount of information. Although I should say Physics Today's target audience is physicists, so we promise reduced technical language. And you just get the entire story. It's accurate and precise. So I want to talk to you a little bit about the process of writing for Physics Today. In the first half of my internship, I worked on an update, which is a 400 to 500 words long story that introduces a recent advancement in the field. Mine was about microcomp integrated silicon photonic systems. Well, the first step of writing an update is searching. It's searching for recently published physics research papers that have relevance to current issues that have not been covered as much and that are just interesting. And then comes the research process. And I can't stress enough the importance of research in just establishing a perspective in your story, because as a science writer, you're not just summarizing the scientific paper, you're also choosing a lens through which to introduce your story so that the audience knows what to do with this new discovery. And of course, just like in every writing project, you got to get the first draft out and out of the way. My published update does not look anything like my first draft. And simultaneous to drafting comes the interview process. You interview the researchers and the experts whose work you're writing about. And I've conducted interviews on the phone, on Zoom, via interview, depending on the availability of the researchers. And I found their input very helpful in clarifying the confusions I had about their methods. And then, of course, there's a ton of editing that goes into drafting an update. I was very lucky to have my mentors, Christine and Andrew. They helped me along the way. They gave me suggestions. They helped me with my edits. And lastly, you confirm your latest update with the researchers just to confirm the accuracy of the story. And then it goes into copy editing. And then you get published. These are my two stories. And of course, depending on the story you're writing, your interview and research processes look very different. I want to share some of the helpful things that I found during my interview in the hopes that you will use them in the future in introducing your work. So the first thing is just shed the jargon. Shed the jargon. I found jargon to be smart. I thought I was giving just the right amount of detail to scientists that I thought would be interested, but it just made my writing unreadable. So this is, at the top, an example from my first draft. We can read it together. Dr. Wang and Dr. Bowers overcame these efficiency and complexity problems by using an aluminum gallium arsenide on-insulator microresonator that is directly pumped by a distributed feedback on-chip laser to generate a dark pulse microcomp. Now, when I read this sentence, I can't visualize what the new discovery is, how it works, how it comes together. But at the bottom, you can see the copy edit version. We used just the right amount of detail. The jargon was reduced, and as you can see, it turned out to be the scientists assembled an aluminum gallium arsenide on insulator microresonator that turned continuous laser light into a coherent microcomp as illustrated above. So we kept the words microresonator and microcomp, which many of you may not be familiar with, but at the beginning of the writing, we gave a definition and a clear explanation as to how they work, as you can see at the bottom. And we also, which you can't see here, we included an illustration just to make it clear to the reader how this new mechanism works. Now I just want to talk to you a little bit about some of the other projects I worked on over the summer. My story on the 52nd International Physics Olympiads was published last Friday. I had the chance to meet the entire US team and the coaches. I also had the opportunity to interview the US and the Japanese academic directors on the last-minute host change from Belarus to Switzerland due to Belarus's involvement in the Russian invasion of Ukraine. Another one of my assignments was to read these 3 books you can see on the screen and write short reviews on them, which we call the book capsules. And my last assignment was to interview the Turkish physicist, experimental particle physicist, Ercan Özcan, who's known for his work at CERN at the Atlas experiment, and also his YouTube collaborations. We talked about his contributions to the industry in Turkey and his manufacturing of tabletop particle accelerators, as well as his recently released YouTube channel. The interview was conducted in Turkish, and then I translated and transcribed it into English. And to conclude my interview, not my interview, my presentation, I've had a lot of interviews, my presentation, I just want to stress the importance of science communication with you all. Researchers rely heavily on the funding we receive from the congressional appropriations and the private enterprises. And so in order to receive and maintain this funding, we have to be able to communicate what our life's work is and how exactly it benefits the public with the taxpayers and their representatives. Our language has to be clear, and we need to develop and master this skill if we want to make sure that the public decisions are informed by science, and just to make sure that our field is accessible and equitable for marginalized groups. Lastly, I want to thank to Brad, Kayla, and Michaela, and Andrew for giving me this opportunity. And I want to thank my mentors and my fellow interns for keeping me company in DC. Thank you so much. And if you have any questions.
Questions? What is one thing that surprised you about the summer internship?
Yes. Well, one thing about physics today is that I didn't know that I'd be doing as much interviews and as much research, as much as just writing and editing. There's a bunch of research that goes into every single story, and you do, if you're doing 100% of the research, only 10% goes into the actual story. So that takes up a lot of time, although it only shows up 10% in your update.
And then question in the back?
Yes.
Of all the different types of stories you worked on, what was your favorite?
Well, my favorite was definitely the microcomb piece that you saw on the left-hand side, because I got to learn a lot about photonics. I didn't know anything about photonics beforehand and how incredibly practical they can be. You can see the piece right here. As I said, I spent half of my internship preparing for the story and writing it and just giving drafts. I think I had 8 drafts in total. So that was pretty interesting.
Round of applause for our speaker.
Thank you all for taking the time to attend these presentations. I'm Matangi, the 2022 AIP FYI intern. I will be presenting what FYI does, how I contributed to it, and why it's an important tool to those in the science policy world. This summer, I interned at FYI, a federal science policy news and resource center at the American Institute of Physics. I was part of a team with Mitch, Andrea, and Will. FYI's primary audience is officials at agencies such as the Department of Energy or the Defense Advanced Research Projects Agency or on Capitol Hill. Here's a deeper dive. So FYI is editorially independent, meaning that its publications are free from the messaging direction of AIP leadership and government relations officials. In addition, FYI aims to present neutral and unbiased information to the science policy community. This allows the FYI audience to take the information at face value and build their own opinions off of the base facts. Scientists are thus empowered to understand and participate in policy processes without formal policy training. FYI is not just a written news service. It also provides science policy bill and budget tracking services. During my internship, I had the opportunity to work on many of the FYI services, including the bill tracker, the This Week blurbs, a bulletin on low-dose radiation research, and most prominently, the budget tracker. The FYI Bill Tracker summarizes and gives context to complicated science policy legislation. It helps FYI's audience to not only understand the legislation, but also identify the significant points of a bill, which may not be immediately evident from the bill's titles. FYI chooses this legislation based on their relevance to science policy, particularly politically salient issues such as climate change and computer technology. Here are some of the bills that I summarized with a particular focus on climate change adaptation. So we have the Federal Agency Climate Act, the Fire Risk Reduction Program Act, and the Science Centers Act. Every Monday, FYI sends out a newsletter called This Week. It includes upcoming science policy events, interesting news articles, job opportunities, and blurbs summarizing the news highlights of the past week. These are the headlines of the blurbs that I worked on, focusing on leadership appointments in science agencies. The blurbs in This Week give FYI's audience the chance to learn about pertinent science policy news in a curated form. All the important news of the week is presented in a one web page concise manner. The blurbs are chosen to also preview the long-form bulletins that we write. For example, I wrote the RICA and low-dose research panel blurbs for leading up to my bulletin on low-dose radiation research. The FYI Bulletin provides long-form articles combining many perspectives to inform the science policy community about current news debates that require a deep dive to understand. These differ from shorter blurbs, not only in length, but in substance, providing context, background, and contrasting opinions in each article. In preparation for my article on the National Academy's Low-Dose Research Report, I read the report and attended the presentation of the report, public comments, and commentary by members of the American Nuclear Society. My most significant project was the budget tracker. The current FYI budget tracker is a set of budget figures from the past few years. Currently, FYI makes these charts every year for the past few years. They're sometimes even used by DOE, NASA, and other officials in their presentations to the science community. My work this summer focused on the expansion of the current tracker to include charts over a longer time period to present the FYI audience with a long-term approach. I primarily focused on numbers for NASA and the Office of Science at the Department of Energy. I collected figures of every sub-agency for the past 10 years of budget justification documents. These figures included the amount the agency requested from Congress, what the House of Representatives proposed, what the Senate proposed, and what was finally enacted. Here are some examples of the charts that I created for the budget tracker using this data. This is the NASA Science Mission Directorate. For those of you who may be unfamiliar, this is a sand or area chart, and each colored section represents a enacted amount for the sub-agencies, and they add up to give the total. And the numbers on the side are represented in billions. And the width, not the slope, represents change over time. And this is the Office of Science enacted numbers. The black dotted line is the total amount that was requested from Congress. And charts like these inform the FYI audience of budget data trends. Here you can see that during the Trump administration years, the request line was much lower for the upcoming fiscal year than the Obama and Biden administration years. This is because DOE expected Congress to not prioritize these projects during that administration. However, Congress continued to provide higher enacted figures during the Trump and Biden presidencies. Here's NASA Science Mission Directorate again, and I've adjusted it for inflation with 2022 numbers. And here's DOE adjusted for inflation. You can see that the red and yellow sections stay similar over time, when previously they appeared to increase. When adjusted for inflation, this information is important to scientists because they can know whether budgets increased, plateaued over time, or just decreased. They can use these charts to compare current proposals to past data and discuss long-term research projects. Throughout the internship and my work on these projects, I contributed these skills to FYI. I found errors from time to time and balanced out the perspective of the rest of the team by encouraging clarity in complex topics for less knowledgeable audience members, like me. I also brought a basic understanding of the federal government, and this, combined with my fast-paced learning skills, was very important to a good internship experience. Throughout the budget project, I gained data analysis skills and learned to use Microsoft Access, a database tool. I also learned how to scan government documents for pertinent budgetary information. Through writing blurbs and in preparation for the bulletin, I learned how to write from a neutral perspective and learned how to use recording tools such as Snagit and Otter AI for transcripts. Thank you, everyone. And overall, I had a great internship experience, and I couldn't have done it without all of you. Are there any questions?
Questions from the audience? What was it like having to adapt your own writing style to the context of your publications?
It was really difficult. I'm a very expressive person when it comes to my writing. I like to put my opinions in there, and so having them have to be from the perspective of FYI, that was difficult, but I really appreciated when Mitch, Andrea, and Will really looked over my writing and gave me the chance to have that neutral perspective. It's a different way of writing. It's not my preferred way of writing, but it's definitely important to know how to do, especially when presenting that unbiased opinion as much as possible.
Any other questions? Real quick.
Okay. I know that when you were reading the policy and correspondences, and I remember at one point you were talking about them being very, I don't know, spicy. So you didn't talk about it with me. I just saw it. So could you maybe say something about that?
Sure. So I did not. One thing that was unexpected about this internship, I really enjoyed looking at the budget documents. And that was pretty unexpected because when you go through a lot of, like Valeria said, it was very dramatic. For example, Congress complains that NASA didn't spend enough money on one thing, or spent too much money on one thing, or moved their window for launching something, and they use words like, "We're very disappointed," or "This was anticipated, but it didn't happen," and they're a real treat. I did not expect that. I thought it would be extremely dry, and there's so much in there.
Round of applause for our speaker.
Good afternoon, everyone. Title of my presentation is Matching with Coding. A quick intro. My name is Saksham Prasapati. I'm an international student over here at States. I'm from Nepal. Over here at State, I'm studying at University of Missouri St. Louis, majoring in astrophysics with a computer science minor. That's me in the background at 4,000 meter altitude in Nepal. So this summer, I'm working with APS Physicists to Go program, where they are matching teachers with physicists. It's like matching a classroom with a physicist. So why are we doing this? We're hoping to bring classroom experience from the physicist point of view. Also, we're hoping that younger generations can have all the exposure to science and also build interest for future STEM-related careers or jobs. So how did we match in the past? We had sign-up forms for teachers and physicists separately on our website of Physicists to Go at aps.org. Once teachers and physicists signed up all those forms, final Excel sheets were created, and all those matchings were done manually. Previously, it was done by an intern, ex-intern, Phoebe. She's a contractor this year. And she looked into all the topics and if all the meeting preferences, if they want prerequisite or live video, and she did all the matching process manually. Once all the matchings were done, they were emailed using mail merger. So some feedback from last year. One was time zone issue. It was mainly from the classroom side, physicist side, sorry. One physicist mentioned that she was having trouble scheduling a visit because she was from California and she got matched with the East Side Coast. Other is science communication. It's mainly from classroom perspective. Physicists were unable to explain, they couldn't remember like what high school level could understand the topic. And other suggestions were to improve process of matching as well. So for our 2022 project, for creating the sign up, we have multiple topic options for teachers. They can select up to 3 choices. We will be matching according to their prioritization from first to third, so that the chances of getting matched would be more. Other is we are adding a time zone option as well, so that they can be matched from their own time zone. And we will also be having the pre-recorded and live video options if they would like, if the physicists would like to present their lectures live in the classroom. And also we're adding school level options if they want middle school or high school. We are hoping that this can minimize the science communication as well, because physicists can choose whatever they are comfortable talking with. And other than that, we will be adding one more question if the teacher has any physics or science class level. This won't be used for matching process, but this would be added for an extra information if they are AP or honors. That's an example of the topics we will be giving. Left side is of physics content topics, and the right side is for application of physics. So fixing with coding. This year I proposed an idea to match all those processes by using a Python program. I chose 4 parameters to all this matching. They were topics, meeting preferences, time zones, and school level. Once all those 4 parameters are matched, an Excel sheet is created, and also I made an email program to email all those match groups automatically. This is just a sample of flow chart. So it goes by row. It checks into the topic sections and school sections, school level section, time zone, and meeting preferences. Once they are passed through the topic sections, the physics data frame are filtered out, and they are also sorted so that the lesser number of topics selected goes at the top. And if all those 4 parameters are matched, then the first row of the filtered out physicist group is matched with the row of the teachers, and they are appended to a list of matched groups, unmatched teachers, and unmatched physicists. And once all the rows are completed and the final Excel sheets are created with 3 different sheets, 3 different tabs, one for matched groups, unmatched teachers, and unmatched physicists. This is just a sample of a screenshot of my script. Left side is the script for the matching process, and the right side is for sending emails. This is a final Excel sheet result, which you will get once the program is completed. You can see the common topics between the teachers and the physicists. For the unmatched teachers, you can see the reason why they were not matched. And the third one is all those leftover physicists. So challenges. Sometimes you don't have to go according to the plan. When I first came to this internship, we had a different set of scope of work. But we had some issues with communication department, and we had to change our idea. That's how I came up with an idea to use the Python programming for the matching process. Python programming was new for me. Even though I was a computer science student, I've never used Python before. My school was based on C++, and I thought this was the best chance to learn this. And Stack Overflow and YouTube were the best source for me. Future physicists go. Claudia, Ali, and I have been planning for our future platforms as well. We are hoping that we can make it more automatic so that less human resource would be used. Our plan is to create profiles for physicists and teachers can go into the website and match, look into the physicists, whoever they like. They can use the filter options, and we are hoping to add a chat within the website itself so that they don't have to exchange contact informations. Thank you.
Questions from the audience?
Was the input in the form of an Excel file as well, or did you use any database?
It was from the Excel file. In Python, it converts into the data frame, and all those processings are done in the data frame itself. Yeah.
So I have one quick question. What's the most important thing that you learned this summer?
That I could work independently. Most of the time, my mentor didn't didn't specify much what I should be working on, and so yeah, working independently.
That is a great answer.
Hi everyone, can you hear me? Okay, excellent. Welcome to my presentation. I'm Lucy Corthell, and I'm a rising junior at Juniata College, and I use she, they pronouns. And I was the Education and Diversity Statistics intern this summer at the American Physical Society, and my mentor was Christine O'Donnell. So this summer I found gaps and inequities in higher education through updating the graphs on the APS Education and Diversity website. So why is that important to APS? Well, part of APS's core values are centered on diversity, inclusion, and respect, highlighted here. But I would say this is relevant to all of you, no matter where you work. You're probably going to have core values or a mission statement that's centered on education or equity, diversity, and inclusion. No matter if you're at NIST, NASA, AIP, AAPT, it's going to be relevant as well as SPS. So here there's a statement on diversity, inclusion, ethics, and responsibility, and just highlighting a section of it. The inclusion of everyone takes many forms and must be an active process that SPS leaders and members adopt. It's encouraged that an SPS chapters and members reach out to all students who might have an interest in physics. So my role was updating, like I said, the statistics, the graphs on the APS website on degrees granted across demographics at US colleges and universities. So I do want to say that when I talk about demographics, I'm specifically talking about race and gender demographics, but there's other demographics to look at as well. These graphs were a great visual representation of the data, and it encourages discussion and shows like obvious trends and disparities. So then you might be asking who exactly is using this data and these graphs that I'm updating. Well, schools can use it to look at how they've done in the past and compare their school to other schools. It's used in grant proposals to increase marginalized populations in STEM and physics. And you and I can use it to just look at our own schools or to educate ourselves and others. And the students and professors use it to maybe write research papers like this one, which was actually written this year, earlier this year. So very relevant. So then how did I collect this data and update the graphs? Well, I used IPEDS, the Integrated Post-Secondary Data System. which is a system of interrelated surveys conducted annually by the U.S. Department of Education's National Center for Education Statistics. And I took data in iPads and I put it into Excel sheets. So now I have a bunch of Excel sheets. What did I do with them? I made an Uber spreadsheet, which is essentially a larger spreadsheet. It's just a massive spreadsheet. And this actually is a tiny portion of the data I worked with. So the Uber spreadsheet is all physics degrees granted across demographics at all physics degree granting universities and colleges. So this specific sheet right here is actually built on 20 years of SPS interns who had my position. So it's building on legacy and expertise. And I used a Python code to essentially put all of the data into this Uber spreadsheet. And I used Emacs and Terminal to access files and edit code. So then what did I find, you might ask? Well, I generated 18 plots, and unfortunately I did find that there continues to be disparities between demographic groups in higher education. This is one graph that is going to be on the website within the next month with the newest data, and this is on bachelor's degrees earned by women, specifically for physics and STEM. And as you can see, there's about 25% of physics bachelor's degrees were earned by women in 2020. And then for STEM, it's about 38%. But looking more at me personally, I'm studying engineering physics, so I wanted to look at engineering statistics. So here's this graph, which I made, and the data is all on the website, so you can download the Excel spreadsheets and make your own graphs if you want. But personally, I took my first engineering class in high school, and I was super excited for it, but I didn't feel included or really part of the class. I was one of 4 women in a class of about 30, and I was like, nope, engineering is not for me. I'm not going to take it again. But the next year, everything else was full, so I had to take it again. And lucky for me, I actually really realized I enjoyed it. I was with a great team, and we worked on some really cool projects. So that leads me to wonder, okay, so if 24% of engineering bachelor's degrees are earned by women, then this data doesn't include women who maybe were physics majors but then felt like they were excluded and changed degrees. So that's why one of my topics that I did this summer was actually reading a lot of papers. Here are some of them that I read. These are education, diversity, and inclusion papers, and essentially they fill in some of the gaps, like the one I just highlighted. That kind of it shares personal testimonies from professors and students on their individual experiences. So that was important. Okay, we're good. So then I'm sure you're asking, what can you do personally to help increase marginalized people joining STEM and physics degrees, and also making the workplace and schools a more inclusive space? So the first step you can do is check out the website, and there's a link. That does have 2018 data because it hasn't been updated for 2 years, but it will in a month include 2020 data. And then you can also, the second step in changing culture and the systemic issues we're facing is acknowledging that there is an issue. So yeah, look at the stats, they're great. And a third step is letting others know about the information. So moving more into that, implementing ways of welcoming marginalized groups in physics and STEM, and amplifying and listening to marginalized groups. So there are free resources for the physics community. I would also recommend that you check those out. So here are references. And I just wanted to thank everyone for this amazing opportunity. Christina O'Donnell, my mentor, the Society of Physics students, Kayla Steffens, Michaela Cleaver, Brad Conrad, and Andrew. It been really awesome. Thanks for organizing so much. And the American Physical Society, APS IT, whenever anything broke, thank you. And the monitor. And of course, all the SPS interns. It's been really wonderful. So thank you. Any questions? Yeah?
Questions?
I was going to say, what would you say like the main takeaway would be from like, what we should take from that?
Yeah, I would say just that there are a lot of inequities and that there's a lot of ways where we can improve. And I mean, yeah, like visiting these resources, I think we can't just say that there are like inequities. We also need to make sure there's an even power balance between different marginalized groups, because if you just have I guess programs which encourage marginalized groups into a school or a place where there's not a power balance, then these students are still, we're still going to feel marginalized and not accepted, and probably more likely to leave the field, whether it's STEM or physics. So, yeah.
One quick one.
Yeah, what are the parameters that go into studying? Like, how does your Uber spreadsheet look like?
The Uber spreadsheet, so essentially it takes, so I download a bunch of Excel files into Google Drive, and then the code like pulls them together. Is that what you're asking?
No, what are the parameters that you're studying for finding out what it is? Like, the categories?
Oh, okay, yeah. So we have all race demographics. Is that what you're asking? And so.
I mean, do you study the economic background and what are all the?
Oh, okay, yeah. So it's just we don't do economic background. So we don't do like low income. Unfortunately, we don't. We also don't do first generation. So that's something that I did analyze. So thanks for asking that question. I put it into like recommendations, and it is something that unfortunately it's not easy to access on iPads. And this like government website, it should be like more straightforward. So we're kind of looking into how then can we look at first generation students and low income students, but it's solely race and gender. So yeah, thank you.
Hello everyone, I'm Katie Futrowski, and I was one of the 2022 AIP Mather Public Policy interns in Representative Bill Foster's office, and I am a rising first year PhD student at Georgia Tech. So my talk will be on the concerning status of climate change legislation and policies in the United States, which happens to be less concerning after news that just happened just a day ago. So first, we want to understand what exactly is causing climate change, and the ultimate driver of climate change is greenhouse gas emissions. And this leads to all of the aspects of climate change that we see, such as hotter temperatures, hotter oceans, sea level rise, more severe storms, drought, poverty, displacement. There's lots of really negative effects of climate change, and we're getting to a point where it's nearing irreversible changes. So, the biggest contributor of this, as I said, is greenhouse gas emissions, which contribute to the greenhouse effect shown here in this diagram. And the biggest greenhouse gas that is causing this is carbon dioxide, and it's been shown that anthropogenic activities are causing this rise in carbon dioxide. The United States happens to be the second largest emitter of carbon dioxide in the world, making it this country's responsibility to mitigate these changes. So we also need to understand how exactly legislation is enacted in the US. And unfortunately, it's a very long process where it results in less than 1% of bills actually being passed into law. So first, a bill is introduced in the House or the Senate. For our purposes, let's say a bill is introduced in the House by a certain sponsor of the bill, or sometimes co-sponsors. Then the bill will be referred to a committee that's related to the topic of the bill. And once the bill is in the committee, it will then be referred to a subcommittee. And the subcommittee has to approve the bill and say that, okay, it's worth actually talking about and considering. So we'll go through this. And then after the subcommittee approves the bill and they go through debate on the different aspects of it, it is then considered again in the full committee. And then if the full committee says, yes, this should be voted on, it is then given to the floor and considered for a full vote by the full chamber. So provided it passes here, this is where it goes to the other chamber, in this case, the Senate, and this whole process is repeated. And after that, a conference committee is convened, and these work to align the bills that passed in the House and the Senate, because to become law, these bills need to have the exact same language. And once that process happens, the bills are again voted on in both chambers. Provided they pass again, the president can sign the bill into law. So now we can ask, what's stopping climate change legislation from being passed in Congress right now? And there are three main things. It's partisanship and divisiveness, and differences among party members, the timing of this legislation, and the long-term nature of climate change. As you can see from these pie charts, both the House and the Senate are basically pretty evenly divided among Democrats and Republicans. And normally, this wouldn't be a cause for any issue preventing legislation from being passed. However, in this era where politics is so controversial and divisive, and where climate change legislation is primarily supported by Democrats, it does make it more difficult for this legislation to get passed. Now, normally, for regular bills, you'd only need a simple majority for these bills to pass, which, by these charts, the Democrats would achieve a very, very slim, simple majority. However, there are many centrist Democrats who don't necessarily agree with their more left colleagues, making this legislation less likely to pass. Again, in the House, at least, they just went into an August recess, and the 117th Congress is nearing its end, making the timing of this legislation a bit difficult. And as I mentioned, the long-term nature of climate change legislation means that Congress members are voting on bills that may not affect them, but will affect generations in the future. So we can ask, where are we now and where are we going? So this is very recent news. In the Senate, climate change legislation is on its path to being passed via a process known as budget reconciliation. Now, what's unique about budget reconciliation bills is that they can't be filibustered in the Senate, meaning that they don't require the 60 out of 100 votes to end cloture and to have the bill move on to consideration. But despite this making it easier for these bills to pass, it's a very cumbersome process, and what's actually about to occur is vote-a-rama, which is a very long period of time, maybe 10 hours, where both House and Senate Congress members are voting on a variety of really controversial parts of these bills, and it's very exhausting. Also, there's very strict rules on what budget reconciliation bills can include via the Byrd Amendment, or the Byrd Rule, which requires these bills to directly change revenue and other related things. And of course, there are issues related to COVID, and then there's the added issue that once this passes in the Senate, it also would need to pass in the House to become law and to pass this climate change legislation. So another big thing, as I mentioned before, is that centrist Democrats need to sign off on this legislation. So up here we have Schumer and Manchin, two faces you've likely seen in the news. They recently finally came to a deal where Schumer is a run-of-the-mill average Democrat, Manchin is a centrist Democrat, and as I showed, you need every single vote you can get to pass this legislation. Now, after Manchin agreed to the deal, we needed Kyrsten Sinema to also agree, and news broke yesterday that she gave the go-ahead. So the executive branch is also considering actions, and that's composed of this guy and a bunch of people under him. So Biden has issued and is considering issuing more executive orders. However, these face questions of legality and whether or not the things he issues in them are under his constitutional power. And then another thing Biden is considering is declaring a climate emergency, which would show the world that we're really taking climate seriously. However, Biden has opted not to do such a thing yet. And we also have an unfortunate attack on climate policies from the judicial branch via the recent West Virginia versus Environmental Protection Agency case, in which the court held that the EPA doesn't have the explicit authority from Congress to cap greenhouse emissions from existing power plants using a generation shifting approach from dirty fossil fuels to clean renewable energy sources. So this did limit the EPA's authority to limit these emissions caps, as I've shown, which are incredibly important for climate change legislation policies. However, the EPA still has authority to set standards for existing power plants as long as it's not through generation shifting approaches, and it will be able to really strictly regulate greenhouse gas emissions of new and future power plants. So to summarize, passing bills is really difficult in Congress in general, but especially in the 117th Congress because it's so evenly divided among Democrats and Republicans, and they don't really get along currently. President Biden can take certain executive actions to combat climate change, but they often face questions of legality. And then finally, the Supreme Court has undermined the EPA's authority to combat climate change and sets a dangerous precedent with its decision in West Virginia versus EPA, but hopefully that'll be a single factor. So thank you to everyone. There's a picture of me with Bill Foster, the representative that I was in the office with, so thanks.
Questions from the audience? So you probably learned lots of things that were surprising over the course of the summer. What's one thing that you were positively surprised about?
Positively surprised about? Oh, that's rough, because Congress is rough. Let's see. Well, it's really cool to just be like in in Congress itself, in the Capitol building. I was surprised that, this sounds a little weird, but that Congress members are indeed people. You don't really realize it, but you're walking down the hallway and there's a bunch of Congress members. In the cafeteria line, I made small talk with someone. I don't know which person he is, but he's a Congress member. So all of that was pretty cool. Just, it really made you feel like you were at the center of like the nation's legislative, power and everything. And it was a really unique opportunity working there.
Round of applause for
All right, can you all hear me okay? All right, good. So we're almost there, right? Just me. The most important thing I learned yesterday during rehearsal is that when you go last, you're the only thing standing between your audience and lunch. And so I'm going to try and keep this as short as I can. So my name is Aiden Keaveney. I am from Appalachian State University in Boone, North Carolina. I am the other AIP Mather Policy intern this summer, also in the office of Congressman Bill Foster. Today, just to end on a high note, I'm going to be talking about the status of nuclear nonproliferation in the era of renewed Russian aggression. So around the beginning of this year, you might have started to see some headlines that look a lot like this about Vladimir Putin changing the status of Russia's nuclear weapons and maneuvering with Russian nuclear forces and things like that, all of which is very scary, particularly my favorite in the bottom right about Russia's Ukraine war ending in disaster, as if it hasn't began in disaster, but I digress. So I will go ahead and spoil this a little bit. We don't expect nuclear war with Russia. You don't need to worry about that. It is very unlikely. Yeah, woohoo. It's very unlikely that Russia will actually act on threats of nuclear war, but the fact that they are threatening nuclear war and the use of nuclear weapons is important in and of itself. And that's sort of the basis of this talk. And the reason why, somebody a lot smarter about this than I am will tell you, this is Secretary of State Antony Blinken. He said this on Monday. So what message does this being Russia's nuclear maneuvering, what does this message send to any country around the world that may think that it needs nuclear weapons to protect, defend, or deter aggression against its sovereignty or independence? It sends the worst possible message. And the German Institute for International and Security Affairs says regional actors with nuclear ambitions such as Iran and Saudi Arabia are watching closely. And so what all of this basically means is that Russia has regional interest, has a regional conflict with Ukraine, and it is using the fact that it has nuclear weapons, these nuclear maneuvers, as if the world would forget that they have nuclear weapons. It's sort of reminding the world that they have nuclear weapons to prevent global action, military intervention on the part of the United States or NATO in Ukraine. And so what does that say to other regional conflicts around the world? So there is sort of a disturbing but not entirely coincidental overlap between some of the biggest border conflicts in the world and nuclear states. So there are currently 9 countries around the world, almost 10 if you count Iran, that have nuclear weapons. 6 of them are on this map and are in some way involved with nuclear weapons, that being Russia, China, India, Pakistan, Israel, and North Korea. The others are the US, the UK, and France. We don't really have any border conflicts, nor does the UK or France. So, but these 6 countries are enough to be concerned about. So Russia obviously has an ongoing regional or border conflict with Ukraine. India and Pakistan have a dispute over the Kashmir region in northern India. Israel has of course border conflicts with the Palestinian territories, But in terms of nuclear security, we'd actually be most concerned about Iran. North Korea has South Korea, and China has Taiwan. All of these countries have potential regional or geographic interest in various land around their borders. And so if you take, for instance, China and Taiwan, which has been in the news lately, if Russia is successful in using nuclear threats to shield themselves from global military intervention, well, that gives China a license to say, well, it worked for Russia and Ukraine. We want to the extent that they don't recognize Taiwan as part of mainland China, which they do, they can say, okay, we're going to start conducting nuclear maneuvers, moving our forces, changing our status alert and whatnot, so that we can reclaim Taiwan without United States intervention, because we have semiconductor interests in Taiwan. There are lots of reasons that the world would want to intervene in this conflict, but we'd be much more hesitant to do so in the presence of nuclear threats. And so that's sort of what we're trying to prevent here. So some things to think about in terms of nuclear nonproliferation. How do we stop the spread of nuclear weapons? In the short term, we want to provide aid to Ukraine, sanction Russia, don't let Russia win. Whatever that means for Russia, which is not entirely clear what their goals in Ukraine are, but whatever that is, don't let Russia be successful. Show that if you're going to use these nuclear threats, if you're going to be aggressive in this way, it's not going to turn out well for you. Even if that's not direct military intervention on the part of the United States or NATO in Ukraine, show Russia that they cannot do this without some kind of consequences. In the medium term, we want to restart negotiations to replace the New START treaty. So since around 2005, the mid-aughts, all of the nuclear nonproliferation treaties on the books have been generally deteriorating. And the last one that is still active is New START. This was extended for 5 years until 2026. In 2021, it cannot be renewed again. And so in 2026, if there are no other nuclear nonproliferation treaties on the books by then, we will again exist in a world where countries around the world have no safeguards from building up their nuclear stockpiles. And that is a big, big problem. And for reference, the original START treaty took 9 years to negotiate. We have 4. And so we need to start talking again, right? We've been talking with Russia basically since the Cold War without stopping until Russia invaded Ukraine. And so we need to start doing that again. This is a separate issue, right? And in the long term, of course, we want to continue to reduce our nuclear stockpiles and advocate for diplomacy in other global conflicts. So I also now just want to talk a little bit about Congressman Bill Foster's leadership on this and how scientists can be leaders on this. So in case you couldn't tell by literally everything going on in this photo, Congressman Foster is a PhD physicist. And he will tell you that during his tenure in Congress, one of his most important roles has been being a translator of science. The story he often tells is about the JCPOA, the Joint Comprehension Plan of Action, better known as the Iran nuclear deal. That when discussions in Congress were going on about the JCPOA, members of Congress would come to him and ask, hey, what is a centrifuge? What is a uranium, right? What does it mean to enrich uranium? Why do we care about 20% enrichment versus 60% enrichment versus 80% enrichment? Scientists need to be in the room to answer these questions. That's why scientists are so important to policy, not just on the member of Congress level, but on the staff level too, on looking at these deals, writing these bills, legislative assistants, directors, staff committee members, all of these things. It's important for scientists to be in the room. In terms of actual legislation, Congressman Foster's focus has been on minimizing the risk of theft and accidents, primarily through tacking on amendments and texts of other bills to various major appropriations packages like the National Defense Authorization Act, the CHIPS and Sciences Act, both of which passed this summer. So I want to leave you with one closing thought about nuclear nonproliferation, which is that scientists created this problem. And so it's up to us to solve it. So thank you to everybody here. Thank you to Team Foster, Congressman Bill Foster, Dr. Mather, who, of course, my internship is named after, and of course the Society of Physics students, all the other interns. Since I'm the last one to go, I'll just go ahead and thank everybody from SPS again for us, because this has been awesome. These guys know I've been wanting to do this internship for years, and it would not be I would not be here were it not for Brad coming to my university and talking about this program, or Kayla and Michaela for interviewing me like 3 times for this. So thank you to everybody who makes this happen. Thank you to all the other interns. This has been a really awesome summer.
Question. What is your one piece of advice to somebody who might want to impact the course of nuclear proliferation?
So the main thing I would say about anything related to science policy in general, is being able to write and communicate effectively. That's the number one thing. If you can talk and you can write, you can do this. And all of you can do that because you are here. In terms of nuclear nonproliferation, specifically, the main thing I think is being aware of this, right? It doesn't get talked about much, and it's sort of, there's a legitimate question, a legitimate debate to be had about whether or not we should talk about this at the risk of it becoming politicized. But being aware of things like the status of the conflict in India and Pakistan, which does not get talked about basically at all in the United States, even though that conflict has been hot for about 20 years. Things about China and Taiwan, which that is becoming, more talked about. Russia and Ukraine, of course. Keeping aware of these things, understanding that there are really, really awful, tragic things related to this going on in the world, and being cognizant of that. It's very easy to sort of, I can't remember if it's a flamingo or an ostrich that kind of puts their head in the sand, It's very easy to do that, but it needs to be sort of understood and talked about. And so those are the 3 things I would say: be able to write, be able to talk, and know what you're writing and talking about.
So I'm actually keeping you from lunch, but thanks, Aiden. So I'm Kayla Stevens. I am the Assistant Director of SPS, and I've had the pleasure of overseeing the SPS Internship Program. And I am so proud, and I can probably speak more than just myself. On behalf of SPS and your mentors and your people you work with, I am so proud of everything you've accomplished in the last 10 weeks, and not just at your placement site, but all the other opportunities that you took advantage of, the relationships that you built amongst each other, and these are lifelong relationships. And for all the other things that you've done. So this may be the closing of the internship program, but it's not goodbye. You are part of the SPS internship family, and you're stuck with us. So I want to give another round of applause to all the interns and all the hard work that they've done this past 10 weeks. And lastly, I would like to thank your mentors, the placement sites, your host institutions, AIP, SPS, and all those who put in so much work to get you here. This program would not be possible without you. So thank you for coming, and thank you all again for all the work that you've done. This program would not be what it is without you. So thank you.